The Big Bang. There was nothing. Not darkness, not silence, not empty space waiting to be filled. None of those things existed yet. Space itself didn't exist. Time didn't exist. The concept of before had no meaning, because there was no clock to measure it against. There was simply nothing. And then, in a way that no human language was built to describe, there wasn't nothing anymore. Everything that has ever existed, every star, every ocean, every thought you've ever had, every person you've ever loved, was compressed into a single point smaller than anything you could point to. Physicists call it a singularity, a place where all the rules of physics collapse into each other and stop making sense. A place where density becomes infinite, where temperature becomes infinite, where mathematics itself shrugs and goes quiet. And then it expanded. Not like an explosion you've ever seen. When something explodes, it expands outward into space that already exists. This was different. Space itself was being created as it grew. Every fraction of a second, there was more universe than there had been before, not because something was moving through emptiness, but because the emptiness was being born in real time. In less than a second, the universe went from something smaller than an atom to something billions of miles across. The heat was incomprehensible. Trillions of degrees. A plasma soup of pure, raw energy, the building blocks of everything churning in a storm that had no eye, no edge, no outside. For the first 3 minutes, not a single atom existed. Just energy. Just chaos. Just the universe screaming itself into existence with nothing to hear it. Then slowly, the temperature dropped enough for the very first protons and neutrons to form. Then electrons. Then, after about 380,000 years a blink, in cosmic time, the first hydrogen atoms stabilized, and the universe, for the very first time, became transparent. Light could finally travel, and it did, in every direction, forever. That light still exists. Right now, as you lie here, there is ancient radiation, leftover warmth from that first impossible moment passing through your body, through the walls of your room, through the earth beneath you. It's called the cosmic microwave background, and it is the oldest thing that can be detected. A whisper from the edge of time itself. You are not separate from that moment. The hydrogen in your body was forged in the first few minutes of the universe's life. The heavier elements were built later in the cores of dying stars. But the beginning is in you. It has always been in you. The universe didn't begin somewhere out there, in some distant corner of space you'll never reach. It began here. It began everywhere. There was no center, because everything was the center. And somehow, after nearly 14 billion years of expansion, cooling, collapsing, burning and exploding, that first moment of nothing becoming, something produced a creature capable of lying still in the dark and wondering how it all started. The universe became aware of itself, and it's still not sure what to make of that. The first stars. For 200 million years, the universe was dark, not metaphorically dark, not dimly lit, completely, totally, perfectly dark. There was no light source anywhere in the observable universe. Just hydrogen gas, that ancient, simple element born in the first few minutes of existence, slowly drifting through an endless black void, pulled in quiet directions by gravity, clumping together in ways too slow and too vast for any human mind to truly picture. This period even has a name. Cosmologists call it the Cosmic Dark Ages, and it lasted longer than the entire current age of the Earth. Think about that for a moment. Twice the age of our planet. Pure, unbroken darkness. No fire, no warmth, no photon of light traveling in any direction from any source. Just cold gas and silence and gravity doing its patient, invisible work. Then something shifted. In certain regions of space, the hydrogen was denser than elsewhere. Gravity pulled harder there. Gas fell inward towards those denser pockets, slowly at first, then faster. The cloud collapsed under its own weight, and as it collapsed, it compressed, and as it compressed, it heated. The temperature at the core of these collapsing clouds climbed slowly, then violently, until it crossed a threshold that changed everything, 100 million degrees. At that temperature, hydrogen atoms stop being hydrogen atoms and start fusing into helium, and fusion releases energy. An enormous, almost incomprehensible amount of energy, enough to push back against the gravity that had been pulling everything inward. For the first time in 200 million years, something pushed back against the dark. The first stars ignited. They were nothing like our sun. They were monsters. Physicists call them population 3 stars, and they were hundreds of times more massive than anything in the sky today. They burned with a ferocity the modern universe no longer produces. They were so hot, so enormous, so luminous that they began tearing apart the hydrogen gas around them, ionizing it, breaking it back down into its raw components in a process called reionization. The cosmic dark ages ended, not with a gentle sunrise, but with a wave of radiation ripping across the universe, clearing the fog, making the cosmos transparent for the second time in its history. And then they died. These first stars burned so bright and so hot that they exhausted their fuel in just a few million years, a cosmic instant. And when they died, they didn't go quietly. Stars that massive collapse and detonate in supernovae, so powerful they briefly outshine entire galaxies. In those deaths, for the first time, heavier elements were forged: carbon, oxygen, iron, gold, things the early universe had never contained. Elements that would eventually drift together, cool, collapse again, and build planets, build oceans, build the proteins inside living cells. Every atom in your body that is heavier than hydrogen or helium was created inside a star that no longer exists. You are made of the ash of the universe's first fires. Those original stars are gone. Not a single one is believed to survive today. They burned too bright, too fast, and left behind only their debris and the darkness they interrupted, which eventually gave way to every light you've ever seen. The universe spent 200 million years in the dark before it learned how to shine. It hasn't stopped since. Dark matter. Most of the universe is missing. Not missing in the sense that we lost track of it. Missing in the sense that we can see its effects everywhere. We can measure the shape it leaves on reality. We can watch the way it bends light and holds galaxies together, and we have absolutely no idea what it is. It doesn't emit light. It doesn't reflect light. It doesn't interact with light in any way we can detect. It passes through ordinary matter, like ordinary matter isn't even there. Right now, at this very moment, it is passing through you, through the walls of your room, through the entire Earth. An invisible river of something we cannot name, flowing through everything, touching nothing. We call it dark matter, and it makes up roughly 27% of the entire universe. Everything you have ever seen, every star, every planet, every galaxy, every atom of everything that has ever existed in any form you could point to, that accounts for less than 5% of what the universe actually contains. The rest is dark matter and something even stranger called dark energy. The universe you can see is a thin film of ordinary matter stretched across an invisible architecture you will never directly observe. Here is how we know it's there. In the 1970s, an astronomer named Vera Rubin was studying the rotation of galaxies. She expected to find what physics predicted, that stars at the outer edges of galaxies would orbit more slowly than stars near the center, the same way planets farther from the Sun move more slowly through their orbits. It's a simple rule. Gravity weakens with distance. Outer stars should lag. They didn't. Stars at the outer edges of galaxies were orbiting just as fast as stars near the core, sometimes faster. By all known physics, galaxies should be flying apart. The visible matter inside them simply doesn't generate enough gravity to hold them together at those speeds. Something else was holding them. Something invisible, distributed in a vast halo around and through each galaxy, providing the gravitational glue that kept everything from scattering into the void. That something is dark matter. And here is the part that should keep you quietly unsettled. We have known about dark matter for decades. Some of the sharpest minds in human history have dedicated their entire careers to identifying what it actually is. Particle accelerators have searched for it. Underground detectors built miles beneath the Earth's surface have listened for it in total silence for years. Space telescopes have scanned for its signature across billions of light years, and we have found nothing. Not a single confirmed dark matter particle. Not one direct detection. It is there. The math is certain. The gravitational evidence is overwhelming. The large-scale structure of the entire universe, the way galaxies cluster into vast filaments and walls, separated by enormous empty voids, only makes sense if dark matter exists and acts as the scaffold everything else was built upon. Without it, the first galaxies could never have formed. The universe would have remained a smooth, featureless fog of gas forever. Dark matter built the skeleton of everything you see. And we cannot see it. You live inside a structure assembled by something invisible and unnamed. The walls holding your reality together are made of something physics hasn't fully explained yet. The universe has a hidden architecture, and we are only just beginning to understand that we are living inside it, small and luminous and ordinary, clinging to the 5% we can see, while the other 95% passes silently through us without leaving a trace. The universe is mostly something we don't have a word for, and it has always been that way. Dark energy. The universe is not just expanding, it is accelerating. Those are two very different things, and the difference between them should unsettle you in a quiet, persistent way. An expanding universe is strange enough. The idea that every galaxy is moving away from every other galaxy, that space itself is stretching like the surface of a balloon, being slowly inflated. That alone takes a moment to absorb. But acceleration means something worse. It means the expansion is speeding up. Every second, galaxies are moving apart faster than they were the second before. Something is pushing. Something is winning against gravity. Something is pulling the universe apart at an ever-increasing rate, and we have no idea what it is. We call it dark energy, and it makes up roughly 68% of everything that exists. Let that settle for a moment. The force actively dismantling the large-scale structure of the universe, the thing driving the single most consequential process happening in the cosmos right now, accounts for more than 2/3 of all the energy in existence. And our best current description of it is essentially, we don't know. It behaves like a property of space itself. As space expands, dark energy doesn't thin out or weaken the way matter and radiation do. It stays constant. More space means more dark energy, which drives more expansion, which creates more space, which creates more dark energy. It is a feedback loop written into the fabric of reality, and it has been running since the universe was roughly half its current age. Here is how we found it. In 1998, two independent teams of astronomers were studying a specific type of exploding star called a Type 1a supernova. These explosions are useful to cosmologists because they always detonate with roughly the same brightness, which means they can be used as distance markers across the universe. By measuring how bright they appear from Earth, you can calculate how far away they are. The teams were using this method to measure the expansion rate of the universe, expecting to find that gravity was gradually slowing things down. Every physicist assumed that gravity, the great attractor, the force that pulls everything toward everything, would be putting the brakes on the expansion left over from the Big Bang. Instead, they found the opposite. The distant supernovae were dimmer than they should have been. They were farther away than the models predicted. The universe wasn't slowing down at all. It was speeding up. Both teams, working independently, arrived at the same impossible answer. The discovery won the Nobel Prize in Physics in 2011, and it left a question at the center of cosmology that has not been answered since. What is pushing? The leading explanation is that dark energy is a cosmological constant, a fixed energy density woven into the structure of empty space, first proposed and then famously abandoned by Albert Einstein, who called it his greatest blunder. It turns out he may not have been wrong, just early. But calling it a constant is less an explanation and more an admission. It means we have measured the effect, given it a symbol in our equations, and moved on without truly understanding what it is or where it comes from. And here is where the scale of this becomes genuinely difficult to hold in your mind. In roughly 2 trillion years, if dark energy continues at its current rate, the expansion of the universe will have carried all other galaxies so far from the Milky Way that they will no longer be visible. The night sky will be empty. Any civilization alive at that point will look out into the cosmos and see nothing but their own galaxy, with no evidence that anything else exists. The rest of the universe will have been swallowed by distance, not destroyed, just unreachable, just gone beyond any horizon that light could ever cross. Dark energy is not violent. It does not tear stars apart or crush planets or announce itself in any dramatic way. It works slowly, quietly, at the largest scales imaginable. It is patient in the way that only something written into the geometry of space can be patient. But it is winning. Gravity pulls everything together. Dark energy pushes everything apart. And right now, at this moment in the universe's life, dark energy is stronger. The galaxies are retreating. The cosmos is thinning. The universe is not collapsing toward some final dense point. It is stretching, cooling, spreading itself across an ever larger emptiness, driven by a force that fills every cubic centimeter of space and answers to nothing. You are living in the brief window of cosmic history where the universe is still populated enough to be beautiful. That window is closing, slowly, imperceptibly, but with the quiet certainty of something that has never once changed its mind. Black holes. There are places in the universe where the laws of physics stop working, not slow down, not bend, stop completely. Places where every equation we have ever written, every model we have ever built, Every framework humans have ever devised to describe how reality operates, all of it breaks down into nonsense at a single point. We know these places exist. We have photographed the shadow of one. We have detected the gravitational ripples produced when two of them collide. They are not theoretical. They are not metaphor. They are real, and they are scattered throughout the universe in numbers too large to count. And at the center of each one is something our mathematics cannot describe. We call them black holes, and the name, for once, is almost honest. A black hole forms when a massive enough star reaches the end of its life and collapses. When a star runs out of fuel, the outward pressure of nuclear fusion, the force that spent millions or billions of years pushing back against gravity, suddenly stops, and gravity, which had been held at bay the entire time, wins instantly. The core of the star collapses inward in a fraction of a second. If the star is massive enough, nothing stops the collapse. Not the pressure of electrons resisting each other, not the pressure of neutrons packed impossibly tight. Nothing. The matter keeps collapsing until it reaches a point of infinite density, a singularity. The same word used for the beginning of the universe, because in both cases the math produces the same answer, infinity, which is physics quietly admitting it doesn't know what happens next. Around that singularity, gravity becomes so extreme that not even light can escape. Light, the fastest thing in the universe, the thing that crosses the observable cosmos in what feels, from its own perspective, like no time at all. Even light, aimed directly away from a black hole's center, curves back, falls in, disappears. The boundary where this happens, the point of no return, is called the event horizon. It is not a surface. It is not made of anything. It is simply a line in space where the escape velocity exceeds the speed of light, and therefore nothing that crosses it can ever return or send any signal back. From the outside, nothing that crosses the event horizon can ever be detected again. It is the cleanest, most absolute disappearance the universe offers. And from the inside, we genuinely don't know. We cannot know. No information escapes. No signal, no light, no particle of any kind has ever returned from beyond an event horizon to tell us what it found. Our physics makes predictions, but those predictions lead to infinities, which is the mathematical equivalent of a blank page. General relativity, Einstein's masterwork, the most precisely tested theory in human history, breaks down at the singularity. Quantum mechanics. The framework that governs the behavior of the smallest things in existence also breaks down there. The two greatest theories humans have ever constructed, each enormously successful in its own domain, become useless at the center of a black hole. They contradict each other. They produce nonsense answers, and we do not yet have a theory that reconciles them. Black holes are, in a very literal sense, the edge of human understanding, but there is something stranger still. In 1974, Stephen Hawking combined quantum mechanics and general relativity carefully at the edges where both still function, and predicted that black holes are not perfectly black, that quantum effects near the event horizon cause them to slowly radiate energy, to evaporate, over time scales so incomprehensibly long they make the current age of the universe look like a single heartbeat. A black hole loses mass, shrinks, and eventually disappears entirely in a final burst of radiation. And here is the problem that Hawking's prediction creates. Everything that ever fell into that black hole, every star, every planet, every atom of everything, is gone The black hole has evaporated. The radiation it emitted carries no information about what fell in. The information about the original matter seems to have been permanently destroyed, but quantum mechanics has a foundational rule, one of its deepest, most unshakable principles, that information cannot be destroyed, ever, under any circumstances. So either Hawking was wrong, or quantum mechanics is wrong, or something happens inside a black hole that neither theory can currently explain, and the resolution to this paradox, called the black hole information paradox, remains one of the most important unsolved problems in all of physics. The universe has placed at the center of its most extreme objects a question it has not yet answered, a place where everything falls in and nothing comes back, a place where our understanding of reality reaches its edge, peers over, and sees only darkness looking back. Neutron stars. There is a point just before complete annihilation where matter makes one final, desperate stand, where gravity has won almost everything, crushed a star, collapsed its core, overcome every force that spent millions of years holding the structure together, and yet something holds. Not comfortably, not peacefully, but with a kind of violent, trembling stubbornness that produces the most extreme object in the universe that still technically qualifies as a thing. Not a black hole, not quite. Something that stopped just short of total collapse and froze there, balanced on the absolute edge of existence, radiating energy and spinning and pulsing in the dark. We call it a neutron star, and almost everything about it sounds like fiction. When a massive star dies, not quite massive enough to form a black hole, but far beyond what our sun will ever be, the core collapses with catastrophic speed. Electrons and protons are crushed together under pressure so extreme they merge into neutrons. The entire core, which may have contained more mass than our sun, collapses in less than a second into a sphere roughly 20 kilometers across. 20 kilometers. You could drive that distance in 15 minutes on an empty road. And yet that sphere contains more mass than the sun. A single teaspoon of neutron star material, scooped up and brought to Earth, would weigh approximately 1 billion tons. Sit with that for a moment. 1 billion tons in a teaspoon. The density is so far beyond anything in ordinary human experience that the comparison almost stops meaning anything. It is the density of an atomic nucleus, the tiny packed core at the center of an atom, scaled up to the size of a city. Neutron stars are, in a very real sense, single enormous atomic nuclei, objects where quantum mechanical rules that govern the behavior of subatomic particles are operating not at the scale of atoms, but at the scale of something you could theoretically see from an airplane. And they spin. This is where neutron stars become something close to beautiful in a terrifying way. Conservation of angular momentum, the same principle that makes a spinning ice skater speed up when they pull their arms in, means that when a star's core collapses from something millions of kilometers wide down to 20 kilometers, whatever rotation it had increases catastrophically. Neutron stars can spin hundreds of times per second. There are neutron stars rotating at over 700 revolutions per second, faster than a kitchen blender, at the scale of a city, with the mass of a star. These rapidly spinning neutron stars emit beams of radiation from their magnetic poles, sweeping across the universe like cosmic lighthouses. When those beams happen to point toward Earth, we detect a precise, rhythmic pulse. We call them pulsars. The first one ever detected in 1967 was so regular and so precise that the astronomers who found it initially labeled it LGM1, Little Green Men, because the signal was so structured, so rhythmic, so unlike anything natural they had encountered, that for a brief moment they genuinely considered the possibility that it was artificial, that something had built it. It wasn't, of course. It was a dead star spinning in the dark with a metronome's precision, doing nothing but existing at the outermost edge of what matter is capable of surviving. There is another variety worth pausing on: magnetars. A magnetar is a neutron star, with a magnetic field so powerful it defies easy comparison. The Earth has a magnetic field. It is useful. It deflects solar wind. It guides compasses. It protects the atmosphere. A magnetar's magnetic field is 1 trillion times stronger. At a distance of half the distance from Earth to the Moon, a magnetar's magnetic field would be strong enough to disrupt the iron in your blood, strong enough to pull the iron out of your body entirely. At closer range, it would distort the electron clouds of your atoms, fundamentally altering the chemistry that makes you possible. You would not burn or freeze or be crushed. You would simply stop being matter in any recognizable form, pulled apart at the quantum level by a field so intense it rewrites the rules of atomic structure. In 2004, a magnetar on the far side of the galaxy, 50,000 light-years away, released a burst of energy in 0.2 of a second that was more powerful than everything our sun will emit over the next 250,000 years. From 50,000 light-years away, it was still measurable. It briefly ionized the upper layers of Earth's atmosphere. A dead star halfway across the galaxy exhaled once, and Earth felt it. Neutron stars are what happens when the universe squeezes matter until it has nowhere left to go but neutrons, packed wall to wall, humming with magnetic fields and spinning in the cold dark at speeds that should not be possible for something that size. They are not the end. They are the moment just before the end. Matter at its most compressed, most extreme, most desperately alive. The last thing a star becomes before it becomes nothing at all. Supernova. Everything you are made of was forged in a dying star. Not metaphorically, not poetically, literally. The calcium in your bones, the iron in your blood, the oxygen filling your lungs right now, none of it existed in the early universe. The Big Bang produced hydrogen and helium, and almost nothing else. The periodic table, that careful inventory of every substance reality is built from, was mostly blank at the beginning. The universe had to learn how to make the rest. And the way it learned was through death, specifically through the most violent, luminous, energetic deaths that matter is capable of producing. A supernova. For most of a star's life, it exists in a state of elegant tension. Gravity pulls inward with everything it has. Nuclear fusion pushes outward with everything it has. These two forces balance each other across millions or billions of years, producing the steady, reliable light that makes planets warm and life possible. But fusion is not infinite. Every star is burning through a finite fuel supply. And as that fuel changes, as hydrogen fuses into helium, helium into carbon, carbon into heavier elements, in sequence the star's internal structure shifts. For the most massive stars, this process accelerates toward a conclusion that cannot be negotiated with. The final stage comes when the core fills with iron. Iron is where fusion stops paying. Every element lighter than iron releases energy when fused. Every element heavier than iron requires energy to be fused. Iron sits at the bottom of the energy curve, the point where the universe stops giving and starts taking. A massive star that has built an iron core has reached the end of its ability to generate outward pressure through fusion. The core, which may contain more mass than our Sun, is now inert. And gravity, which has been held back for millions of years, does not hesitate. The collapse takes less than a second. In that fraction of a second, the iron core, roughly the size of Earth, collapses to the size of a city. The density becomes nuclear. The collapse is so sudden, so violent, that the outer layers of the star, still falling inward, hit the newly formed neutron star core and bounce. The rebound sends a shock wave outward through the star at a significant fraction of the speed of light, and the outer layers of the star, everything above the core, everything that was the star's body for millions of years, are blasted outward into space. The energy released in this moment is almost impossible to hold in the mind. In the first 10 seconds of a supernova, more energy is released than our Sun will emit over its entire 10-billion-year lifetime. For weeks afterward, a single exploding star can outshine its entire host galaxy, hundreds of billions of stars combined. If a supernova occurred within a few hundred light-years of Earth, the radiation would be sufficient to strip away the ozone layer, expose the surface to lethal ultraviolet radiation, and trigger a mass extinction. Some researchers have proposed that certain mass extinctions in Earth's past may have had exactly this cause: a star dying somewhere in the neighborhood, and life on Earth paying the price. But here is the paradox at the heart of all of this. Those same deaths are the reason life exists at all, in the extreme temperatures and pressures of a collapsing, exploding star in the shock wave, tearing outward through layers of gas at unimaginable speeds. Elements heavier than iron are forged for the first time. Gold, platinum, uranium. The heaviest atoms in existence, created in the most violent moments the universe produces, scattered across space in the explosion's wake. This debris drifts, cools, mixes with hydrogen clouds across millions of years. And eventually, gravity pulls those enriched clouds together again into new stars, new planets, new chemistry. The solar system you live in was built from the remnants of stars that died before the Sun was born. There is a specific type of supernova worth pausing on, the one mentioned earlier in the story of dark energy's discovery, a Type 1. A supernova occurs not in a single massive star, but in a binary system, where a white dwarf, the dense, cooling remnant of a smaller dead star, slowly steals mass from a companion star until it crosses a precise threshold and detonates. Because they always detonate at roughly the same mass, they always produce roughly the same brightness. They are the universe's standard candles, reliable enough to measure distances across billions of light-years, precise enough to reveal that the expansion of the cosmos is accelerating. A dead star exploding with metronomic consistency, used as a ruler to measure the shape of everything. Even in death, stars do useful work. The universe has no recycling program in any gentle sense. It does not quietly compost its dead. It detonates them. It flings their contents across light years at a fraction of the speed of light, seeds the void with complexity, and waits for gravity to pull the pieces back together into something new. Every heavy atom in your body passed through the heart of a dying star before it found its way to you. You were assembled from shrapnel, from the debris of something enormous that ended so that something smaller and stranger could begin. You are not just made of stars. You are made of their last moments. Galaxies, the universe is not evenly filled with stars. If you could step back far enough that individual stars became invisible, far enough that entire solar systems were too small to register, you would see something that looks almost biological. Not a smooth, uniform glow spread evenly across space, but a vast, tangled web of bright filaments and dense nodes threaded through an immensity of emptiness. Clusters of light separated by voids so enormous that if you placed our entire solar system inside one, it would be indistinguishable from nothing. The universe, at its largest scales, looks less like a scattered field of light and more like a structure. Like something organized. Like a web spun by a process so large and so slow that no human civilization will ever watch it complete a single motion. The nodes of that web are galaxies. A galaxy is, at its simplest, a gravitationally bound collection of stars, gas, dust, and dark matter. But that description is like describing a cathedral as a collection of stones. It captures the inventory without touching the reality. The Milky Way. Our galaxy, the unremarkable spiral we call home, contains somewhere between 100 billion and 400 billion stars. That range exists not because we haven't counted carefully enough, but because counting individual stars in a galaxy is genuinely beyond current technology. We estimate, we model, we use statistics and light curves and mass calculations. And the answer we arrive at is hundreds of billions, and the Milky Way is not especially large. The observable universe contains an estimated 2 trillion galaxies. 2 trillion, each one containing hundreds of billions of stars, each star potentially hosting planets, each planet sitting inside a solar system with its own particular chemistry, its own particular history, its own particular silence or noise. The numbers become unusable at a certain point. They stop producing awe and start producing a kind of cognitive blankness, the mind reaching for a handhold and finding nothing to grip. 2 trillion galaxies is not a fact that can be felt. It can only be noted and then quietly set aside because the human brain was built for savannas and small groups and distances you could walk in a day. Galaxies come in shapes. Elliptical galaxies are the oldest and largest smooth, featureless, reddish collections of ancient stars that have long since exhausted their gas and stopped forming new ones. They are retirement communities for stars, quiet, vast, slowly fading. Spiral galaxies like our own are younger and more active, with sweeping arms of gas and dust where new stars are still being born, blue and hot and short-lived, lighting up the edges of the spiral in colors that photographs make look almost painfully beautiful. Irregular galaxies have no particular shape at all, often the result of collisions, their structure scrambled by gravitational encounters with neighbors, their star formation thrown into chaotic bursts by the disruption. And galaxies collide, not rarely, not catastrophically, in the way collisions usually work. When 2 galaxies meet, the individual stars almost never actually strike each other. The distances between stars within a galaxy are so vast that even in a merger, the probability of direct stellar collision is low. Instead, galaxies pass through each other like 2 swarms of fireflies walking through the same space, each firefly too far from the others to touch. What does collide, violently and consequentially, is the gas. Enormous clouds of hydrogen and dust smash together, triggering massive bursts of star formation. Gravity warps the shapes of both galaxies, pulling out long tidal tails of stars that stretch across hundreds of thousands of light-years. The entire process takes hundreds of millions of years, a slow-motion catastrophe that looks, in time-lapse simulations, like two luminous ghosts merging into one. The Milky Way is currently on a collision course with the Andromeda Galaxy. In approximately 4.5 billion years, the two largest galaxies in our local group will begin their merger. The night sky, if anyone is alive to see it, will gradually fill with the spreading glow of Andromeda approaching. Over billions of years, the two galaxies will pass through each other, separate, fall back together, and eventually merge into a single large elliptical galaxy that astronomers have already informally named Milky Way. Our Sun will almost certainly survive. Statistically, it is unlikely to be involved in any direct stellar encounter, but the Milky Way, as a structure, as a shape, as the spiral pattern of light that has arched over every human being who has ever lived on this planet, will cease to exist. Everything your ancestors saw when they looked up at the night sky will be gone, replaced by something larger, something quieter, something without arms. There is something worth sitting with in the fact that galaxies, these structures containing hundreds of billions of stars, spanning hundreds of thousands of light years, persisting for billions of years, and still subject to gravity, still fall toward each other, still merge and reshape and reorganize across timescales that dwarf the entire history of life on Earth. Nothing in the universe is too large to be pulled. Nothing is too vast to be changed. Everything, at every scale, is still in motion. The islands of light are drifting, some toward each other, some carried by dark energy away forever. The ocean of nothing between them grows larger every second, and the lights, seen from far enough away, look almost warm. The Milky Way. You live inside a galaxy, not near one, not orbiting one from a safe observational distance, inside one. Embedded within it, roughly 2/3 of the way out from the center, along one of its spiral arms, a modest position, neither central nor peripheral, neither especially dangerous nor especially interesting by cosmic standards. You cannot see your galaxy the way you see other galaxies in telescope photographs, spread across the frame in their full spiral glory, because you are inside it. Trying to understand the shape of the Milky Way from Earth is like trying to understand the layout of a city from a single room within one of its buildings. You can see the walls around you. You can see the sky above. But the full shape, the full structure, requires a perspective you cannot reach. Everything you have ever known exists inside this single structure. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped region of stars from which the spiral arms extend, rather than arms emerging directly from a smooth central bulge. It spans roughly 100,000 light-years across. Light, the fastest thing in the universe, traveling at 300,000 kilometers per second, would take 100,000 years to cross it from edge to edge. Our solar system sits in a region called the Orion Arm, a minor spiral arm, unremarkable in its position and composition, orbiting the galactic center at a speed of roughly 800,000 kilometers per hour. At that speed, one trip around the center of the Milky Way takes approximately 225 million years. That unit of time even has a name, a cosmic year, one galactic orbit. The last time our solar system was in its current position relative to the galactic center, the most complex life on Earth was a reptile. Dinosaurs had not yet appeared. The Permian extinction, the largest mass dying in Earth's history, which wiped out over 90% of all species, had just occurred. The Earth was geologically almost unrecognizable, and our solar system has completed barely 20 of these orbits since it formed. In galactic terms, We are young residents of a very old structure. At the center of the Milky Way sits something that took decades to confirm and longer to accept. A supermassive black hole. It is called Sagittarius A star, and it contains the mass of approximately 4 million suns, compressed into a region smaller than our solar system. For decades it was inferred its presence felt through the behavior of stars orbiting the galactic center at extraordinary speeds, tracing tight ellipses around an invisible point of enormous gravity. Then, in 2022, the Event Horizon Telescope collaboration published the first direct image of it, a blurry ring of orange light surrounding a central darkness, the shadow of a black hole 4 million times more massive than our Sun, sitting at the heart of the galaxy you live in. Every star in the Milky Way orbits it, including ours. The Sun, and everything gravitationally bound to it, every planet, every moon, every asteroid, every comet, every particle of dust in the entire solar system, and every living thing that has ever existed on Earth is in a slow, enormous orbit around a supermassive black hole 250,000 light-years away. This fact was not known to any human being until the 20th century. Every civilization that ever rose and fell on this planet, every empire and religion and philosophy and war, unfolded inside a structure whose nature and center were completely unknown to the people living within it. We named the stars before we knew what they were. We built calendars around their movements before we understood what was moving what. The Milky Way has satellite galaxies, smaller galaxies, gravitationally bound to it, orbiting it the way moons orbit planets. The large and small Magellanic Clouds, visible from the southern hemisphere as faint smudges of light, are the most prominent of these. They are being slowly consumed. The Milky Way's gravity is pulling streams of gas from them, incorporating their material into its own structure. In the far future, they will be absorbed entirely, not in a violent collision, but in a slow gravitational inhalation, the larger galaxy quietly taking what it wants from the smaller ones. The Milky Way is, by any honest accounting, an ordinary galaxy, not the largest, not the most massive, not unusually active or unusually ancient. There is nothing in its composition or structure that marks it as special in the catalogue of 2 trillion galaxies that populate the observable universe. It has a supermassive black hole at its center, as most large galaxies do. It has spiral arms, as many galaxies do. It has a history of merging with smaller galaxies, as most large galaxies do. It formed from the same processes, follows the same physics, will end in the same merger with Andromeda that galactic dynamics made inevitable billions of years before Earth existed. And yet, inside this ordinary galaxy, on an ordinary arm, orbiting an ordinary star, on a small rocky planet with liquid water and a thin atmosphere and a moon just the right size to stabilize its axial tilt, something happened that has not been confirmed to have happened anywhere else in the observable universe. Matter became aware of itself. Life appeared, looked around, built tools, asked questions, lay down in the dark, and wondered about the structure it was embedded in, unable to see the full shape of its own home, piecing together the picture from light that traveled hundreds of thousands of years to reach it. The Milky Way does not know we are here, but we know it is there. And for now, in the absence of any confirmed alternative, that exchange, however one-sided, remains one of the most remarkable things this universe has managed to produce. The solar system. The solar system did not have to exist, not in this configuration, not with this particular arrangement of planets, this particular distance from the galactic center, this particular balance of rocky inner worlds and gas giant outer worlds that happened to produce the conditions for the only confirmed life in the universe. The process that built it was not careful. It was not guided. It was a chaotic, violent, largely random cascade of physics, gas collapsing, rocks colliding, planets migrating, bodies being flung inward and outward, and sometimes entirely out of the system, and the version we ended up with is not the only version that could have emerged from that initial cloud of gas and dust. It is simply the version that survived its own formation. And surviving formation, it turns out, is not trivial. About 4.5 billion years ago, a cloud of gas and dust enriched with heavy elements from generations of dead stars began to collapse. The trigger may have been a nearby supernova, its shock wave compressing the cloud past the threshold where gravity could take over. The cloud collapsed inward, conservation of angular momentum causing it to spin faster as it shrank, flattening into a rotating disk with a dense, hot center. That center accumulated more and more mass until pressure and temperature crossed the threshold for nuclear fusion. The sun ignited, and the leftover material in the disk around it began the long, chaotic process of becoming everything else. In the early solar system, the disk was a demolition derby. Dust grains stuck together into pebbles. Pebbles accumulated into rocks. Rocks collided and sometimes shattered and sometimes stuck, growing into bodies called planetesimals, irregular, crater-pocked objects ranging from meters to kilometers across, swarming in their millions through the young disk. These planetesimals continued colliding and accumulating, and the larger ones grew faster because their gravity was stronger, pulling in more material with each passing orbit. This runaway growth produced the planetary embryos, moon-sized and Mars-sized bodies, that then began colliding with each other in impacts so enormous they melted entire worlds and sent debris spraying across the inner solar system. The Earth you live on is the product of several of these catastrophic mergers. But the solar system's story is not simply one of local chaos. The giant planets, Jupiter most consequentially played a role in shaping everything. Jupiter's gravity is immense enough to have prevented the asteroid belt from ever accumulating into a planet. The material between Mars and Jupiter was perpetually stirred and scattered by Jupiter's gravitational influence before it could coalesce. Jupiter also acted as a partial shield for the inner solar system, its gravity deflecting or capturing some of the comets and asteroids that might otherwise have struck the inner planets with far greater frequency. The Earth has been hit by large impactors many times. Without Jupiter, the rate may have been dramatically higher. There is a theory, the grand tack hypothesis, that Jupiter did not always orbit where it does today. That in the early solar system, Jupiter migrated inward, moving towards the Sun, before being caught by Saturn's gravitational influence and pulled back outward. This inward and outward migration, the grand tack, named after a sailing maneuver, may have sculpted the inner solar system dramatically, explaining why Mars is smaller than models predict, why the asteroid belt is relatively sparse, and why the rocky inner planets have the particular sizes and compositions they do. Jupiter moving inward and then retreating may have been a prerequisite for Earth becoming habitable. A gas giant's migration, billions of years ago, may be part of the reason you exist. The outer solar system is stranger and more populated than the version taught in school. Beyond Neptune lies the Kuiper Belt, a broad ring of icy bodies, remnants of solar system formation, including Pluto and dozens of other dwarf planets. Beyond that, At distances almost incomprehensible even by solar system standards, lies the Oort cloud, a vast, diffuse shell of icy objects extending perhaps a quarter of the way to the nearest star. The Oort cloud has never been directly observed. Its existence is inferred from the long-period comets that occasionally fall inward towards the Sun, their orbits suggesting they originate from an enormous distant reservoir. The solar system extends, in this tenuous and invisible way, to distances that make the orbits of the planets look like a small, tight cluster near the center. The solar system is vast beyond the scale of ordinary imagination, and yet it is nothing compared to the distances between it and its nearest neighbors. The nearest star system, Alpha Centauri, is 4.2 light-years away. In the units of the solar system, that is roughly 260,000 times the distance from Earth to the Sun. The solar system, for all its scale, is a tiny island of gravitational influence surrounded by an ocean of interstellar space that dwarfs it entirely. We have sent probes into that ocean. Voyager 1, launched in 1977, is the most distant human-made object in existence. It has been traveling for nearly 50 years, moving at speeds that would cross the continental United States in a few minutes, and it has only just barely crossed the heliopause, the boundary where the Sun's solar wind gives way to interstellar space. At its current speed, it would take 70,000 years to reach Alpha Centauri if it were aimed in that direction. It is not aimed in that direction. It is simply moving outward into the interstellar void, carrying a golden record containing sounds and images from a planet that may no longer be recognizable by the time anything encounters it. A message in a bottle, thrown into an ocean so large that the concept of finding it requires timescales longer than human civilization has existed. The solar system, formed by accident, survived its own chaotic birth by a combination of physics and fortune, arranged itself into a configuration that happened to produce the conditions for liquid water and complex chemistry, and then, 4.5 billion years later, produced a species that launched a small metal object into the void with a record of its music attached, not because it would likely be found, but because the alternative saying, nothing, felt worse. The Sun. Every morning, without ceremony, you are bathed in the light of a nuclear explosion, not the aftermath of one, not the residual warmth of something that burned out long ago. An active, ongoing, continuously detonating thermonuclear reaction happening right now, 93 million miles away, converting 5 million tons of mass into pure energy every single second. The light touching your skin this morning left the surface of the Sun 8 minutes ago. The energy that produced it was generated in the Sun's core approximately 100,000 years ago, spending that vast stretch of time slowly, violently, bouncing outward through layers of dense plasma before finally escaping into space, and, after 8 minutes of unobstructed travel, arriving at your window. The Sun is not a ball of fire. Fire is a chemical reaction, molecules breaking apart and recombining, releasing energy stored in chemical bonds. The Sun operates at a completely different level of physics. At its core, the temperature reaches 15 million degrees Celsius, and the pressure is 340 billion times the atmospheric pressure at Earth's surface. Under those conditions, hydrogen nuclei, single protons, move fast enough and press close enough together to overcome their natural electromagnetic repulsion and fuse. 2 protons fuse into deuterium. Deuterium fuses into helium-3. Helium-3 fuses into helium-4. And at each step, a tiny fraction of mass is converted directly into energy according to the most famous equation in physics. That fraction is small, only about 0.7% of the original mass becomes energy. But the amount of hydrogen undergoing fusion in the Sun's core every second is so enormous that 0.7% of it represents 5 million tons of mass vanishing into pure energy every second. Every second, without pause, without interruption, for the last 4.5 billion years. The Sun has consumed roughly half its hydrogen fuel since it formed. It sits comfortably in the middle of its main sequence life, the long, stable phase where hydrogen fusion in the core maintains the equilibrium between gravity and outward pressure. This stability is not permanent, but it is extraordinarily long-lived by any scale that matters to life. The Sun will continue fusing hydrogen in its core for approximately another 5 billion years. In human terms, it is middle-aged, reliable, predictable, a machine that has been running without meaningful interruption since before the Earth existed. But the Sun is not static, and it is not entirely benign. The surface of the Sun, the photosphere, churns at roughly 5,500 degrees Celsius, covered in convection cells, each roughly the size of Texas, rising and falling as hot plasma moves upward, cools, and sinks again in a continuous roiling motion. Above the photosphere lies the chromosphere, and above that the corona, a region of superheated plasma extending millions of kilometers into space, somehow hotter than the surface below it, which defies simple intuition and remains an active area of research. The corona is the source of the solar wind, a continuous stream of charged particles flowing outward from the Sun in every direction, filling the entire solar system, sweeping past every planet, eventually thinning out at the heliopause where interstellar space begins. The solar wind touches Earth constantly. Earth's magnetic field deflects most of it, bending the charged particles around the planet, protecting the atmosphere and the surface from direct exposure. Where the magnetic field lines converge at the poles, some particles spiral in and collide with atmospheric molecules, producing light, the aurora borealis, the aurora australis. The most beautiful light show on Earth is a byproduct of the Sun trying to strip away the atmosphere and the planet's magnetic field pushing back. The Sun is also capable of more violent outbursts. Sunspots, dark regions on the solar surface where intense magnetic field lines suppress convection and cool the local area, are sites of stored magnetic energy. When that energy releases suddenly, it produces solar flares, intense bursts of radiation, traveling at the speed of light that reach Earth in 8 minutes. More dangerous still are coronal mass ejections, where billions of tons of magnetized plasma are hurled into space at millions of kilometers per hour. When a large coronal mass ejection strikes Earth's magnetic field, it can induce electrical currents in power grids, damage satellites, disrupt communications, and in extreme cases cause widespread infrastructure failure across entire continents. In 1859, a coronal mass ejection known as the Carrington event struck Earth with a force that set telegraph wires on fire, produced auroras visible at the equator, and disrupted global communications for days. The technological civilization of 1859 was primitive enough to absorb it. A comparable event today, striking a world dependent on satellites, power grids, and digital infrastructure, would cause damage estimated in the trillions of dollars and potentially take years to fully recover from. The Sun does not target Earth. It does not aim. It simply exhales in all directions constantly, and Earth happens to be in the way. The Sun's eventual death is worth understanding, because it reframes everything. In approximately 5 billion years, the hydrogen in the Sun's core will be exhausted. Fusion will shift to a shell around the core, and the increased energy output will cause the Sun's outer layers to expand dramatically. The Sun will become a red giant, swelling outward to roughly 200 times its current radius. Mercury and Venus will be consumed entirely. Earth's fate is uncertain. The Sun's outer atmosphere may reach Earth's current orbit, or Earth may have already migrated outward as the Sun loses mass. Either way, the oceans will have boiled away billions of years before the expansion reaches its maximum. The surface of the Earth will be scorched, barren, unrecognizable long before the Sun physically engulfs it. After the red giant phase, the Sun's outer layers will drift away into space, a slow, glowing cloud of gas called a planetary nebula, nothing to do with planets, despite the name. And what remains at the center will be a white dwarf, a dense, slowly cooling ember, roughly the size of Earth, containing half the Sun's remaining mass, no longer fusing anything, simply radiating its stored heat into space across billions of years until it fades to black. The Sun will not explode. It is not massive enough for a supernova. It will simply expand, shed its outer layers, and quietly cool into darkness over timescales that make the entirety of human history invisible. But right now, it is burning. Right now, it is converting 5 million tons of itself into light and heat every second, sending that energy across 93 million miles of empty space, warming the surface of a small rocky planet just enough to keep liquid water stable, just enough to drive weather and seasons and photosynthesis, just enough to make the particular chemistry of life possible. You are alive because a star is slowly destroying itself at a controlled rate 93 million miles away. And it has been doing this without acknowledgement, without interruption, since long before anything on Earth existed that could notice. Planetary Formation. Every world begins as dust, not metaphorically, not as a poetic shorthand for something more complex. Literally, as dust, microscopic grains of rock and ice and carbon, drifting in the cold outer regions of a collapsing gas cloud, too small to see individually, too numerous to count, suspended in the disk of material left over after a young star ignites at the center. These grains are the raw ingredients. They are the starting point, and the process that turns them into something as large and complex and geologically active as a planet is one of the most violent, wasteful, and improbable construction projects the universe runs. It begins with sticking. Dust grains collide constantly in the protoplanetary disk. Most collisions are gentle enough that the grains adhere van der Waals forces, the same weak molecular attraction that allows geckos to walk on ceilings, hold them together. Grains become clumps. Clumps become pebbles. Pebbles accumulate into loose, irregular aggregates that drift slowly through the disk, sweeping up material as they go. This early phase is slow and fragile. The growing bodies are not yet large enough to have meaningful gravity. They are held together by weak molecular forces and the gentle dynamics of the disk, and they are perpetually at risk of being shattered by slightly too energetic a collision. There is a point in this process that planetary scientists find genuinely difficult to explain, the meter-size barrier. Once growing bodies reach roughly a meter in diameter, they enter a regime where they are large enough to be significantly affected by gas drag from the disk, but not yet large enough for their own gravity to help them accumulate more material. Bodies of this size spiral inward towards the young star rapidly in as little as a few hundred years before they can grow further. The early solar system should, by simple physics, have lost most of its solid material to the Sun before planets could form. And yet planets formed. The exact mechanism by which bodies survived and grew past this critical size range is still an active area of research. Several solutions have been proposed. Streaming instabilities, where particles concentrate into dense filaments that collapse directly into larger bodies under their own gravity, bypassing the meter-size problem entirely. The universe found a way. It almost always does. Once bodies reach kilometer scale, gravity begins to matter. A kilometer-sized planetesimal has enough gravitational pull to attract nearby material, and the larger it grows, the stronger its attraction becomes. This produces a runaway effect. The biggest bodies grow fastest, sweeping up smaller ones in a cascade that, over millions of years, produces a relatively small number of large planetary embryos from an initial population of countless smaller bodies. These embryos, roughly moon-sized to Mars-sized, then enter a phase of giant impacts. They collide with each other in events so energetic that entire worlds melt. Rocky mantles vaporize, iron cores merge. The heat generated by these impacts is sufficient to produce global magma oceans, where an entire planet's surface is molten rock, churning and radiating heat into space as it slowly cools. The Earth passed through this phase. What you walk on is the cooled surface of a world that was once entirely molten. The continents, the ocean floors, the mountain ranges and valleys, all of it, is the solidified crust of a planet that formed in fire, settled over hundreds of millions of years into something stable enough for liquid water to persist, and then spent the next 4 billion years being shaped by the geological forces that liquid water and internal heat produce. The inner and outer solar system formed differently. Close to the young sun, temperatures were too high for water and volatile compounds to condense into solid form. Only rock and metal could solidify in the inner disk, which is why the inner planets are small, dense, and rocky. Mercury, Venus, Earth, Mars, all built from the materials that could survive the heat of the young sun's neighborhood. Further out, beyond what planetary scientists call the snow line, the distance at which water ice can stably exist in the disk, a much wider range of materials were available in solid form. Water ice, ammonia ice, methane ice. The abundance of solid material beyond the snow line allowed planetary cores to grow faster and larger, and once they crossed a threshold of roughly 10 Earth masses, their gravity became strong enough to capture hydrogen and helium directly from the disk, the lightest and most abundant elements in the universe, which had been unavailable to the inner rocky planets. This is how gas giants form. Jupiter and Saturn are not simply large rocky planets. They are rocky and icy cores that grew large enough, fast enough, to capture enormous envelopes of hydrogen and helium before the young sun's radiation blew the remaining disk material away. The timing was critical. The disk of gas and dust surrounding a young star persists for only a few million years before stellar radiation disperses it. Gas giants had to form within that window. Rocky planets had more time. They continued accumulating material through impacts for tens of millions of years, but gas giants had to build their cores and capture their atmospheres before the gas was gone. Jupiter formed first and fastest. It consumed the most material. It established the gravitational architecture of the outer solar system, while the inner solar system was still a churning population of embryos and planetesimals. Everything that came after every planet, every moon, every asteroid and comet, formed in the gravitational landscape that Jupiter created. Moons form through variations on the same processes. Some are captured objects, bodies, that formed independently. and were captured by a planet's gravity. Some formed from the same disk of material that surrounded a forming gas giant, and some formed from impact debris material blasted off a planet by a giant collision, falling into orbit and slowly accumulating into a satellite. The Moon belongs to this last category, and its story will get its own chapter. But the principle applies broadly. The violence of planetary formation generates debris, and debris generates moons, and the solar system ended up with a collection of natural satellites that in some cases, Titan, Europa, Ganymede, are larger than planets. The solar system we inhabit is not the product of a clean, orderly process. It is the survivor of a chaotic selection worlds that formed, collided, migrated, scattered, and were sometimes ejected entirely from the system. The planets that exist today are the ones that found stable orbits after billions of years of gravitational negotiation. The ones that didn't are gone, consumed by the sun, merged into larger bodies, or flung into interstellar space to wander alone forever. Every world that exists is a survivor, including this one. The dust that drifted in the cold outer regions of a gas cloud 4.5 billion years ago did not know what it would become. It had no direction, no intention, no awareness of the extraordinary chain of collisions and accumulations and catastrophic impacts that would eventually produce a planet with oceans and weather and a biosphere complex enough to produce something capable of looking up and asking where it came from. The answer, it turns out, is chaos. Chaos and enough time and gravity pulling everything toward everything else until something resembling order emerged from the wreckage. Earth. There is one planet in the observable universe that we know with absolute certainty harbors life. One out of the 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially hosting multiple planets, across a total number of worlds so large it dissolves into abstraction. We have confirmed life on exactly one of them, this planet, the one you are lying on right now. And the more carefully science examines the conditions that made Earth habitable, the longer the list of requirements becomes. Not a short list of obvious factors, liquid water, breathable air, but a deep, precise, almost suspiciously specific list of conditions that had to be met simultaneously, maintained over billions of years, that conspired together to produce the only confirmed living world in the observable universe. Earth is not typical. Begin with the location. The solar system sits in a relatively calm region of the Milky Way, far enough from the dense, radiation-intense galactic center to avoid the elevated rates of supernovae and gravitational disruption that would periodically sterilize a planet. Close enough to the center that the interstellar medium is enriched with heavy elements from generations of dead stars, providing the raw materials for rocky planets and complex chemistry. This region, sometimes called the galactic habitable zone, is not where most stars reside. It is a particular band of the galaxy, and our solar system happens to occupy it. Then there is the Sun itself, a stable, middle-aged star of a particular type not too large, which would mean a shorter and more violent life, not too small, which would mean a planet would need to orbit so close to stay warm that tidal locking and stellar flares would make the surface hazardous. The Sun is the right size, the right age, the right temperature. It has been stable enough, for long enough, to allow 4 billion years of uninterrupted biological evolution. A star that varied significantly in output over that timescale, that had major outbursts or dimming events that dramatically altered the energy reaching Earth's surface, would have repeatedly disrupted or destroyed complex life before it had time to establish itself. Then there is the distance. Earth sits within the habitable zone, the range of orbital distances from the Sun where liquid water can exist on a planet's surface given sufficient atmospheric pressure. Venus, closer in, experienced a runaway greenhouse effect that boiled its oceans and baked its surface to nearly 500 degrees Celsius. Mars, farther out, lost its atmosphere and its liquid water to the cold and the solar wind. Earth, between them, maintained liquid water on its surface for 4 billion years. This is not guaranteed. It requires the right atmospheric composition, the right reflectivity, the right geological processes to regulate temperature over geological time. Earth has all of these. Venus and Mars do not. The size of Earth matters too. Large enough to retain a substantial atmosphere through its own gravity, unlike Mars, which lost most of its atmosphere because its gravity was insufficient to hold it against the solar wind after its magnetic field weakened. Large enough to maintain geological activity, the internal heat that drives plate tectonics, which is itself a key factor in Earth's habitability. Small enough that it did not capture an enormous hydrogen and helium envelope like the gas giants, which would have produced a crushing, uninhabitable atmosphere with no solid surface. Plate tectonics deserves particular attention. Earth is one of very few planets in the solar system confirmed to have active plate tectonics, the process by which the solid outer shell of the planet is divided into moving plates that collide, separate, and slide past each other, driven by convection in the mantle below. This process does more than produce earthquakes and volcanoes. It acts as a long-term thermostat for the planet. Carbon dioxide in the atmosphere, a greenhouse gas that warms the surface, is absorbed by rainwater, which weathers rocks and carries carbon into the ocean as carbonate minerals. Those minerals are eventually subducted into the mantle at plate boundaries, where they are heated and release carbon dioxide back into the atmosphere through volcanic activity. This carbon cycle, operating over millions of years, has regulated Earth's temperature through ice ages and warm periods, through changes in solar output, through the rise and fall of entire ecosystems. Without plate tectonics, the carbon cycle breaks. Venus has no active plate tectonics. Its carbon dioxide stays in the atmosphere, accumulating over billions of years, producing the runaway greenhouse effect that made its surface lethal. Earth avoided this fate, not simply because of its distance from the Sun, but because it has a geological system capable of regulating its own atmospheric chemistry over time scales long enough for life to develop and persist. Then there is the magnetic field. Generated by the movement of molten iron in Earth's outer core, the magnetic field extends far into space, forming a protective bubble called the magnetosphere that deflects the solar wind, the continuous stream of charged particles streaming outward from the Sun. Without it, the solar wind would slowly strip away the atmosphere, the way it stripped away much of Mars's atmosphere after Mars's own magnetic field weakened billions of years ago. The magnetosphere is not visible. It produces no light, no sound. It simply exists, invisibly, deflecting the Sun's outpouring of charged particles day and night, year after year, allowing the atmosphere to persist and the surface to remain habitable. You are alive, in part, because of a process happening in molten iron thousands of kilometers below your feet. The Moon's role is significant and underappreciated. Earth's axial tilt, the angle at which the planet's rotational axis leans relative to its orbital plane, is responsible for the seasons. A planet with no axial tilt has no seasons. A planet with an extreme, wildly varying axial tilt experiences catastrophic seasonal swings that make large portions of the surface periodically uninhabitable. Earth's axial tilt is currently about 23.5 degrees, which produces seasons mild enough for life to persist across most latitudes. And that tilt is stable, kept from wandering chaotically by the gravitational influence of the Moon, which is large enough relative to Earth to act as a stabilizer. Computer models of Earth without the Moon suggest the axial tilt could vary dramatically over millions of years, producing climate instability severe enough to repeatedly disrupt the biosphere. The Moon is not merely a feature of the night sky. It may be a prerequisite for the stability that allowed complex life to evolve. And yet for all of this, the right location, the right star, the right distance, the right size, the right geological activity, the right magnetic field, the right moon. The Earth has also been repeatedly struck by large impactors, experienced multiple mass extinctions that wiped out the majority of species alive at the time, passed through global glaciation events where ice may have covered the surface from pole to equator, and endured enormous volcanic episodes that filled the atmosphere with toxins and reshaped the climate for hundreds of thousands of years. Life survived all of it. Not the same life. Not the same species, or even the same phyla in some cases. But life as a process. The chemistry of self-replication and metabolism and adaptation never stopped. It persisted through the worst the planet could produce, diversified into the spaces opened by each catastrophe, and eventually produced, in one particular lineage of upright primates, something capable of reconstructing the entire history of the planet it was born on. Earth is not special because the universe designed it to be. It is special because an almost incomprehensible number of conditions converged, by physics and chance and deep time, to make it briefly, improbably, stubbornly alive. How many other places in the universe share that convergence, we do not yet know. But we know of one, and you are on it. The Moon. The Moon should not exist. Not in the way it does. Not at this size, not at this distance, not with this particular composition that so closely mirrors Earth's own mantle material, while being mysteriously depleted of certain elements that Earth possesses in abundance. When planetary scientists first began seriously analyzing the Moon's chemistry, when the Apollo missions returned samples, and those samples were studied in detail, the results did not fit neatly into any of the then existing models of lunar formation. The Moon was too big to have been captured from elsewhere. Its composition was too similar to Earth's to have formed independently in a different part of the solar system, and it contained too little iron relative to Earth to be simply a chunk of the early Earth that had somehow been spun off. The Moon's existence is a problem that required an extraordinary solution. The solution, now broadly accepted among planetary scientists, is called the giant impact hypothesis, and it is exactly as dramatic as the name suggests. Approximately 4.5 billion years ago, roughly 100 million years after the solar system formed, the young Earth was struck by another planet, not an asteroid. Not a comet, a planet. A body roughly the size of Mars, about half the diameter of Earth, on an orbital path that brought it into direct collision with the early Earth. Planetary scientists have given it a name, Theia, and the collision it produced was not a glancing blow, not a near miss that left both bodies shaken, but intact. It was a direct, catastrophic impact that released energy orders of magnitude beyond anything that has struck Earth since. The impacting body did not bounce off. It did not simply crater the surface. It merged with the Earth, its iron core sinking into Earth's own core. its mantle material mixing with Earth's mantle in the violence of the impact, while an enormous plume of vaporized rock was blasted outward into space. That vaporized rock, ejected into orbit around the newly merged Earth, formed a disk of debris. And that disk, over thousands of years, accumulated under its own gravity into the Moon. This is why the Moon's composition mirrors Earth's mantle so closely, because it is largely made of Earth's mantle, blasted into space by an impact so violent it momentarily vaporized rock across a significant fraction of the planet's surface. This is why the Moon is depleted in volatile elements, because the extreme heat of the impact drove off lighter compounds before the debris could coalesce. This is why the Moon has a relatively small iron core, because Thayer's iron had already sunk into the merged Earth's core before the debris was ejected. The giant impact hypothesis explains the Moon's peculiarities with a single catastrophic event, but the implications extend far beyond explaining the Moon's chemistry. The impact itself had profound consequences for the Earth. The merger of two planetary bodies released enough energy to melt the entire planet, producing the global magma ocean that Earth passed through in its early history. The collision also set the Earth spinning faster than it rotates today. In the immediate aftermath of the impact, an Earth day may have lasted as little as 5 hours. Over billions of years, tidal interactions between Earth and Moon have slowed Earth's rotation and simultaneously caused the Moon to gradually spiral outward to its current distance. This process continues today. The Moon moves approximately 3.8 centimeters farther from Earth each year. The Moon you see in the sky tonight is not the same distance away as the Moon your ancestors saw. It is slightly imperceptibly farther. When the Moon formed, it was perhaps 10 times closer to Earth than it is today. The tides it produced at that distance would have been enormous, not the gentle twice-daily rhythms of the modern ocean, but massive, powerful surges reshaping coastlines and churning the shallow seas where, billions of years later, life would first appear. Some researchers have proposed that the energetic tidal mixing of the early ocean played a role in the origin of life, that the repeated concentration and dilution of chemical compounds in tidal zones created conditions favorable for the self-assembly of the first replicating molecules. The Moon's gravitational influence on the early Earth may have been not just a backdrop to life's origin, but an active ingredient. Then there is the axial stabilization discussed in the previous section. Without the Moon's gravitational steadying influence, Earth's axial tilt could wander chaotically over millions of years. The climate stability that allowed complex multicellular life to evolve over hundreds of millions of years, the relatively predictable cycling of ice ages and warm periods, the persistence of habitable zones across broad latitudes, may depend on the Moon keeping Earth's tilt within a manageable range. A planet that periodically tilted dramatically, experiencing centuries where the poles faced the Sun and the equator, was plunged into darkness, would present a profoundly different evolutionary environment, perhaps not impossible for life, but dramatically more challenging. The Moon also makes possible something that has punctuated human history across every culture on every continent: total solar eclipses. The Moon is 400 times smaller than the Sun and approximately 400 times closer to Earth. This extraordinary coincidence, a ratio that holds almost exactly, means that from Earth's surface, the Moon and the Sun appear nearly identical in size. During a total solar eclipse, the Moon fits almost perfectly over the disk of the Sun, blocking its light entirely, while leaving the corona, the Sun's outer atmosphere, visible as a ghostly halo around the darkened disk. This phenomenon is unique in the solar system. No other planet has a moon in this precise size and distance relationship with its star. It is entirely coincidental, and it is also temporary. Because the moon is slowly moving away, in 50 million to 600 million years, depending on the calculation, the moon will have receded far enough that it will no longer be large enough in the sky to fully cover the sun. Total solar eclipses will cease to exist. Any civilization alive at that point will have missed them, will have no direct experience of the most visually dramatic astronomical event visible from Earth's surface, will know them only from records left by whatever came before. We happen to live in the brief window of Earth's history when total solar eclipses are possible. That window is closing. The moon hangs in the sky tonight at a distance that took a planetary catastrophe to achieve. Its presence steadies the planet beneath you, pulls the oceans twice a day, slows the Earth's rotation with patient inevitability, and produces, on rare and predictable occasions, a darkness in the middle of the day that has stopped armies, inspired religions, and driven human beings to travel to remote corners of the planet just to stand in a shadow that lasts, at most, a few minutes. Something the size of Mars hit the Earth 4.5 billion years ago. The debris formed the moon. The moon made the planet stable enough, and the tides energetic enough, and the conditions specific enough, that billions of years later, something on Earth's surface could look up at night and see it hanging there, enormous and silver and close, and feel without knowing exactly why that it matters. It does. More than almost anything else in the solar system, it matters. Plate tectonics. The ground beneath you is not still. It has never been still, not once in the entire 4.5 billion year history of this planet has the surface of the Earth held its position. The continent you are lying on right now is moving slowly, imperceptibly, at roughly the speed your fingernails grow, but moving with a force and a consequence so vast that it has reshuffled the entire surface of the planet multiple times, built and eroded mountain ranges taller than the Himalayas, opened and closed ocean basins, triggered ice ages, driven mass extinctions, and created the particular arrangement of land and sea that every living thing on Earth has adapted to over millions of years. The world map you learned as a child is a snapshot, a brief, temporary configuration of a surface that has looked completely unrecognizable for most of Earth's history and will look completely unrecognizable again in the deep future. The arrangement of continents you think of as permanent, the shape of Africa, the position of the Americas, the particular outline of coastlines that appear on every globe and atlas has existed in roughly its current form for only a tiny fraction of Earth's history. Before it, there were other arrangements, other supercontinents, other ocean configurations, other climate patterns produced by different distributions of land and sea, and before those, others still. The surface of the Earth is not a fixed stage on which life performs. It is itself a dynamic, shifting actor in the story. The mechanism behind all of this was not understood until the 1960s. For most of human history, the shapes of the continents were simply accepted as given as permanent features of a static Earth. The resemblance between the coastlines of South America and Africa was noticed and remarked upon for centuries, but the idea that the two continents had once been joined and had drifted apart was considered fringe science for decades after it was first formally proposed. Alfred Wegener, a German meteorologist, published his theory of continental drift in 1912, arguing that the continents had once formed a single landmass he called Pangaea and had since drifted apart. His evidence was compelling, not just the matching coastlines, but matching geological formations on opposite sides of the Atlantic, identical fossil species found on continents now separated by thousands of miles of ocean. But he could not explain the mechanism. He could not say what force was moving continents through the solid rock of the ocean floor. He was ridiculed by much of the scientific establishment. He died in 1930 on an expedition to Greenland before the mechanism was discovered. It took another 3 decades of ocean floor mapping, paleomagnetic studies, and the discovery of mid-ocean ridges for the scientific community to assemble the full picture. By the late 1960s, the theory of plate tectonics had replaced continental drift, not just explaining that the continents moved, but explaining precisely how and why. The surface of the Earth is divided into roughly 15 major plates, rigid slabs of rock, some carrying continents, some forming ocean floors, all moving relative to each other, driven by convection in the mantle below. The mantle is not liquid in the way water is liquid. It is solid rock that over millions of years flows like an extraordinarily slow, viscous, fluid-hot material rising from depth, spreading laterally, cooling, and sinking back down in a cycle that drags the plates above it in different directions. Where plates move apart, magma rises to fill the gap, creating new ocean floor in a process called seafloor spreading. The mid-Atlantic ridge, running down the center of the Atlantic Ocean, is the boundary where the North American and Eurasian plates are separating. New rock is being created there continuously, pushing the 2 plates apart at a few centimeters per year. Iceland sits directly on this ridge, one of the few places on Earth where a mid-ocean spreading center is visible above sea level, expressed as volcanic activity and geothermal heat, and a landscape that looks geologically newborn. Where plates collide, the results depend on what is colliding. When 2 continental plates meet, neither subducts easily. Continental rock is too buoyant to sink into the mantle. Instead, the collision crumples both plates upward, building mountain ranges. The Himalayas are the product of the Indian plate colliding with the Eurasian plate, a collision that began roughly 50 million years ago and continues today, still pushing the Himalayas upward by a few millimeters each year. The mountain range you think of as ancient and permanent is geologically young, still actively growing, the product of a collision that began long after the dinosaurs were gone. When an oceanic plate meets a continental plate, the denser oceanic plate subducts, slides beneath the continental plate, and sinks into the mantle. This subduction produces some of the most dramatic geological features on Earth. Deep ocean trenches mark the lines where oceanic plates descend. Volcanic arcs form inland, where the subducting plate releases water and other volatiles into the mantle above it, lowering the melting point of the rock and producing chains of volcanoes. The Pacific Ring of Fire, the chain of volcanic and seismic activity encircling the Pacific Ocean, is the surface expression of subduction occurring around the edges of the Pacific Plate. Subduction also drives the carbon cycle discussed in the Earth section. Carbon-rich sediments on the ocean floor are carried down with the subducting plate, heated in the mantle, and eventually returned to the atmosphere as carbon dioxide through volcanic activity. This geological recycling of carbon operating on time scales of millions of years has regulated Earth's atmospheric composition and surface temperature through changes in solar output, through ice ages, through the evolution of photosynthetic life that dramatically altered atmospheric chemistry. Plate tectonics is not just a geological process. It is a planetary climate regulation system, a thermostat built into the structure of the Earth's interior, operating continuously and invisibly beneath every human civilization that has ever existed. And it has not operated smoothly. The history of plate tectonics is punctuated by episodes of dramatic, consequential activity. Large igneous provinces events where enormous volumes of magma erupted over relatively short geological timescales, flooding millions of square kilometers with lava, have repeatedly altered the atmosphere, releasing vast quantities of carbon dioxide and sulfur dioxide, triggering warming events, ocean acidification, and mass extinctions. The Siberian Traps, a large igneous province that erupted approximately 252 million years ago, is the leading candidate for the primary cause of the Permian extinction, the largest mass dying in Earth's history, which eliminated over 90% of marine species and 70% of terrestrial vertebrate species. A geological process, a planetary-scale volcanic event, and 90% of ocean life gone. The continents are currently in a configuration that is, by geological standards, temporary. In approximately 250 million years, current plate motions will have carried the continents into a new supercontinent configuration. Several models exist for what this will look like: Pangaea Proxima, Orica, Amasia, each based on different extrapolations of current plate velocities and directions. The details are uncertain. The general outcome is not. The Atlantic Ocean will close. The Americas will collide with Africa and Europe. The particular geography that every human civilization has ever known, the coastlines, the mountain ranges, the ocean basins, will be unrecognizable. Whatever exists on the surface of the Earth in 250 million years will look up at a night sky containing a slightly different arrangement of nearby stars, stand on a continent that shares no borders with any country that has ever existed, and have no direct experience of the world that was here before. The ground beneath you has always been moving. It moved while your ancestors built their cities on it, drew their borders across it, buried their dead in it. It moved while every species that has ever lived on this planet evolved and went extinct on its surface. It will move long after the last living thing on Earth has gone, reshuffling the surface with patient, geological indifference, long past the point when there is anything left to notice the change. You are not standing on solid ground. You never were. The atmosphere. If you scaled the Earth down to the size of a basketball, the atmosphere would be thinner than a coat of paint, not thinner than a sheet of paper, thinner than the paint applied to the surface of the rubber. That thin layer, that almost imperceptible coating on a basketball-sized planet, is the only thing separating every living thing that has ever existed on this world from the hard vacuum of space. From temperatures that swing between 270 degrees below zero and over 100 degrees above, depending on whether sunlight is hitting you or not. From cosmic radiation that would damage DNA at lethal rates. From the unfiltered solar wind that would strip the oceans away over geological time. From the silence and cold and emptiness that constitutes the vast majority of the universe's volume. Everything you have ever known exists inside a thin smear of gas clinging to a rock. The atmosphere was not always this way. The Earth's original atmosphere, the one that existed when the planet first formed, was almost certainly a dense mixture of hydrogen and helium, the most abundant elements in the solar system. But the young Earth was not massive enough to hold these light gases against the solar wind and the heat of the young sun, and they were stripped away relatively quickly in geological terms. What replaced it was an atmosphere produced from within, outgassed from the planet's interior through billions of years of volcanic activity. This second atmosphere was dominated by carbon dioxide, nitrogen, water vapor, and sulfur compounds. There was virtually no free oxygen. If you had been transported to the early Earth and removed your helmet, you would have died immediately not from cold or heat, but from asphyxiation and carbon dioxide poisoning on a planet that, from space, looked not entirely unlike home. Oxygen came later, and its arrival was catastrophic. Roughly 2.5 billion years ago, a group of microorganisms called cyanobacteria developed the ability to perform oxygenic photosynthesis, to split water molecules using sunlight and release oxygen as a byproduct. For millions of years, this oxygen was absorbed by dissolved iron in the oceans, producing the banded iron formations visible in ancient rock layers today. But eventually the iron was saturated, and oxygen began accumulating in the atmosphere. To the anaerobic microorganisms that dominated life at the time, organisms that had evolved in a world without free oxygen, for which oxygen was toxic, this was a planetary catastrophe. The Great Oxidation Event, approximately 2.4 billion years ago, likely drove the majority of anaerobic life to extinction or to the oxygen-free refuges where their descendants still live today. One organism's waste product was another's atmosphere. The oxygen that fills your lungs right now, the molecule your cells depend on for the energy metabolism that keeps you alive, is the accumulated byproduct of billions of years of photosynthetic life altering the chemistry of an entire planet. You breathe the exhaust of ancient microorganisms. The atmosphere is not a natural feature of a rocky planet. It is a biological artifact. It was built by life, and it is maintained by life. And without the continuous activity of photosynthetic organisms, it would shift over geological time back toward something unbreathable. The atmosphere is divided into layers, each with its own character. The troposphere, the lowest layer, extending roughly 12 kilometers above the surface, contains approximately 75% of the atmosphere's total mass and virtually all of its weather. Every cloud, every storm, every hurricane and blizzard and gentle afternoon rain occurs within this thin lower layer. The air thins rapidly with altitude. At the summit of Everest, roughly 9 kilometers above sea level, the atmospheric pressure is about a third of what it is at sea level. Climbers at that altitude are operating at the edge of what human physiology can sustain without supplemental oxygen, breathing air so thin that each breath delivers a fraction of the oxygen available at the surface. Above the troposphere lies the stratosphere, and within it, a molecule that deserves particular attention. Ozone. The ozone layer, a region of relatively elevated ozone concentration in the stratosphere, absorbs the majority of the sun's ultraviolet radiation before it reaches the surface. Ultraviolet radiation damages DNA. At the doses that would reach the surface without the ozone layer, exposure would make the development of complex surface life extraordinarily difficult. The ozone layer is not thick. The total amount of ozone in the atmosphere, if compressed to surface pressure, would form a layer roughly 3 millimeters deep. 3 millimeters of a trace gas, distributed through the stratosphere, is the difference between a surface habitable for complex life and one that is not. In the 1980s, scientists discovered that a class of synthetic chemicals, chlorofluorocarbons, used in refrigerants and aerosol propellants, were destroying ozone molecules in the stratosphere at rates that were measurably thinning the layer, particularly over Antarctica. The Antarctic ozone hole, documented and tracked through the decade, represented the first instance in which human industrial activity was demonstrably altering a planetary-scale atmospheric system in ways that threatened the habitability of the surface. The Montreal Protocol, signed in 1987, phased out the production of the most damaging chemicals. The ozone layer has been slowly recovering since. It remains one of the clearest examples of a global environmental problem identified, addressed, and meaningfully improved within a human lifetime. The atmosphere also acts as a thermal blanket. Greenhouse gases, carbon dioxide, water vapor, methane, nitrous oxide absorb infrared radiation emitted by the warmed surface and re-emit it in all directions, including back towards the surface. This greenhouse effect is not inherently harmful. Without it, Earth's average surface temperature would be approximately -18 degrees Celsius, well below the freezing point of water across most of the planet, likely incompatible with the liquid water that life depends on. The natural greenhouse effect is what makes Earth habitable. The problem is not the mechanism, but the concentration. Adding greenhouse gases to the atmosphere increases the warming effect. The carbon dioxide concentration in the atmosphere has increased from roughly 280 parts per million before industrialization to over 420 parts per million today, higher than at any point in the last 3 million years. The atmosphere has changed before, and dramatically. The carbon dioxide levels of the deep past have been far higher than today. The temperature swings of ice ages and warm periods have reshaped ecosystems and driven species extinctions repeatedly. The atmosphere is not fragile in the sense of being easily destroyed. It has survived asteroid impacts, massive volcanic episodes, and the rise of oxygen-producing life. But it is sensitive. Small changes in composition produce large changes in temperature and chemistry, and it responds on timescales that are short by geological standards, but long relative to human civilization. Changes set in motion today will play out over centuries. The atmosphere is where weather happens, where climate is regulated, where the chemistry of life is maintained, where the dangerous radiation of space is absorbed, where the last molecules of breathable air give way to the hard vacuum of the cosmos above. It is the boundary between everything and nothing, and it is thinner, relative to the planet it protects, than you will ever quite be able to make yourself believe. Breathe in. What fills your lungs right now is ancient. It has been breathed before by every human being who has ever lived, by every animal that has ever existed on this planet, by creatures so alien to your biology that you would not recognize them as life if you saw them. The nitrogen in your next breath has cycled through the atmosphere for billions of years. The oxygen was released by photosynthetic organisms over geological time, accumulated slowly in a world that had never known it, and eventually reached a concentration that made your kind of life possible. You are not breathing air. You are breathing history. Oceans. 71% of this planet's surface is covered in water. Not damp, not moist. Covered. Submerged beneath an average depth of 3.7 kilometers of liquid water. A global ocean so vast that if you flattened every mountain and filled every trench to make the Earth a perfect sphere, the ocean would cover the entire surface to a depth of over 2 kilometers. There would be no land, no coastlines, no beaches or river deltas or continental shelves. Just a planet entirely wrapped in water, blue and featureless from space, with no dry surface anywhere. This is the planet you actually live on. The land feels dominant because you live on it. Because human civilization, almost without exception, developed on the 30% of the surface that sits above sea level. But the ocean is not a feature of Earth. The ocean is Earth. The land is the exception, elevated fragments of continental crust poking above a global water world, surrounded on all sides by a connected body of water so immense that it shapes the climate, drives the weather, regulates temperature, produces the majority of the oxygen in the atmosphere, and harbors the majority of the planet's biomass. And we have explored less of it than we have explored the surface of the Moon. The ocean's origin is still debated in its details. The early Earth was hot, too hot for liquid water to exist on the surface for hundreds of millions of years after formation. The water that eventually formed the oceans came partly from volcanic outgassing, water vapor released from the planet's interior through billions of years of geological activity, and partly, researchers believe, from the delivery of water-bearing asteroids and comets during the period of heavy bombardment that characterized the early solar system. The exact proportions are uncertain. What is known is that by approximately 4 billion years ago, liquid water was present on Earth's surface and has remained there continuously ever since. 4 billion years of uninterrupted ocean. The deep ocean is perhaps the least understood environment on Earth. The Hadal Zone, the deepest portions of the ocean, found in the Great Ocean Trenches, reaches depths of nearly 11 kilometers in the Mariana Trench, the deepest point on Earth's surface. At those depths, the pressure is over 1,000 times the atmospheric pressure at the surface, enough to crush unprotected submarines, enough to compress the human body to a fraction of its surface volume in an instant. The temperature is just above freezing. No sunlight penetrates. No photosynthesis occurs. And yet life exists there, organisms adapted to darkness and crushing pressure and near-freezing temperatures, living on the slow rain of organic material sinking from the sunlit layers above. Life at the deep ocean floor does not depend on sunlight. This realization, which became concrete with the discovery of hydrothermal vent ecosystems in 1977, fundamentally altered the understanding of where life can exist. Hydrothermal vents are cracks in the ocean floor where geothermally heated water, rich in dissolved minerals, vents into the cold, deep ocean. The temperature gradient between the superheated vent water and the surrounding cold creates chemical energy gradients that chemosynthetic bacteria exploit using chemical reactions rather than sunlight to produce energy, forming the base of entire ecosystems. Tube worms meters long, eyeless shrimp, ghostly fish, dense colonies of microorganisms all thriving in total darkness, kilometers below the surface, powered entirely by the heat of the Earth's interior. This discovery had implications that extended far beyond Earth. If life can exist without sunlight, sustained entirely by chemical energy from geological processes, then the range of environments in the universe where life might persist expands dramatically. Europa, a moon of Jupiter, has a global ocean of liquid water beneath an icy crust, kept liquid by tidal heating from Jupiter's gravity. Enceladus, a moon of Saturn, actively vents water vapor and organic molecules from its subsurface ocean into space through cracks in its icy surface. The Cassini spacecraft flew through these plumes and detected complex chemistry. Both worlds have liquid water. Both worlds have geological activity. Both worlds, by the logic of hydrothermal vent ecosystems, are candidates for life. The oceans also drive Earth's climate in ways that are easy to underestimate. Water has an extraordinarily high heat capacity. It absorbs and stores heat far more effectively than rock or air. The oceans absorb the majority of the excess heat produced by the enhanced greenhouse effect, buffering the rate of atmospheric warming. They also circulate that heat globally through a system of currents driven by differences in temperature and salinity, the thermohaline circulation, sometimes called the ocean conveyor belt. This circulation moves warm surface water from the tropics toward the poles and returns cold, deep water towards the equator, moderating temperatures across vast regions of the planet. The Gulf Stream, A component of this system carries warm tropical water northward along the eastern coast of North America and across the North Atlantic, keeping Western Europe significantly warmer than it would otherwise be at its latitude. London sits at roughly the same latitude as Calgary. The reason London's climate is mild and Calgary's winters are severe is ocean circulation, the movement of warm water across the Atlantic, releasing heat into the atmosphere, keeping the Western European climate habitable for the civilization that developed there. Remove or significantly weaken the thermohaline circulation, and European temperatures could drop dramatically within decades. There is evidence from past climate events that exactly this has happened, that rapid freshwater input from melting ice sheets has disrupted the circulation, triggering rapid regional cooling even as global temperatures were rising. The ocean's chemistry is changing. Carbon dioxide dissolving into seawater forms carbonic acid. The ocean absorbs roughly a quarter of all human carbon dioxide emissions, moderating atmospheric accumulation but acidifying the water in the process. Since industrialization, ocean pH has dropped measurably, a small change in absolute terms, but enormous in its biological consequences, because the organisms that build shells and skeletons from calcium carbonate, corals, mollusks, many species of plankton find it harder to maintain their structures in more acidic water. The base of the marine food web is built on organisms that are sensitive to pH changes, that are, by human sensory standards, completely undetectable. Somewhere in the ocean, roughly 4 billion years ago, chemistry crossed a threshold. Molecules began replicating themselves. The precise location and mechanism remain debated. Hydrothermal vents are one candidate. Warm, shallow tidal pools influenced by the moon's enormous early tides are another. But wherever it happened, something that had previously been simple chemistry became something more. It became a process that copied itself, that varied, that competed, that accumulated complexity over time. It became, in the most fundamental sense, life. Everything that has ever lived on this planet traces its ancestry to that moment. Every tree, every insect, every fish, every bird, every human being who has ever drawn breath, all of it descended from whatever first crossed that line in whatever corner of the early ocean it occupied. The entire biosphere, every ecosystem on land and sea, every metabolic pathway, every genetic code is the elaboration of a chemistry that began in water and has never fully left it. Your cells are mostly water. Your blood is chemically similar to seawater. The fluid inside your cells maintains an ionic composition that reflects the ocean chemistry of the ancient world in which your most distant ancestors evolved. You left the ocean hundreds of millions of years ago. You have never entirely left. The origin of life. At some point, something happened that has never been fully explained, not poorly understood, not partially mapped, not explained in broad strokes with a few details still to fill in. Genuinely, fundamentally, at the deepest level of scientific inquiry, not yet explained. The origin of life, the transition from chemistry to biology, from complex molecules arranging and rearranging themselves according to physical laws to molecules that replicated, varied, and accumulated complexity across time, is one of the most important unsolved problems in all of science. We know it happened. We know roughly when. We know some of the chemical building blocks involved. We do not know how they assembled into the first living thing, or what that living thing looked like, or exactly where on the early Earth it happened. What we know is that 4 billion years ago, the Earth was a very different place. The atmosphere contained no free oxygen. The oceans were chemically rich, full of dissolved minerals, metal ions, organic compounds delivered by meteorites, and produced by geological activity. The young moon was close, producing enormous tides that rhythmically covered and exposed coastal and tidal environments. Hydrothermal vents on the ocean floor created steep temperature and chemical gradients. Ultraviolet radiation from the sun, unfiltered by an ozone layer that did not yet exist, hammered the surface. Lightning split molecules in the atmosphere. Volcanoes injected chemicals into the air and sea continuously. It was a world of extreme energy and chemical complexity. And somewhere in that world, the first step toward life occurred. One of the earliest clues came from a laboratory experiment in 1952. Stanley Miller, a graduate student working under Harold Urey at the University of Chicago, assembled a simple apparatus, a flask of water, a mixture of gases thought to represent the early atmosphere, electrodes to simulate lightning, and a condenser to cycle the resulting compounds back through the system. He ran the experiment for a week. When he analyzed the contents, he found amino acids, the molecular building blocks of proteins, the workhorses of biochemistry, complex organic molecules, essential to life as we know it, had assembled spontaneously from simple chemistry in less than a week. The Miller-Urey experiment did not create life, but it demonstrated something profound, that the gap between simple chemistry and the building blocks of biology is not as vast as it might seem. The universe tends toward organic chemistry. Amino acids have been found in meteorites, in interstellar clouds, in the dust surrounding distant stars. The raw ingredients of life appear to be common. The universe manufactures them readily. What remains unexplained is the next step. How did those ingredients assemble into something that could replicate itself? The central problem is this. Life as we know it runs on two types of molecules, proteins and nucleic acids. Proteins do the work of the cell, catalyzing reactions, building structures, transporting molecules. Nucleic acids, DNA and RNA, store and transmit the information needed to build proteins. But proteins cannot replicate without nucleic acids to carry their instructions, and nucleic acids cannot be built without proteins to catalyze the reactions. Each requires the other. How did this chicken and egg system arise from chemistry that had neither? The leading current answer centers on RNA. RNA is a simpler molecule than DNA, capable of both storing information and, in certain forms, catalyzing chemical reactions. RNA molecules that catalyze their own replication ribozymes have been produced in laboratory conditions. The RNA world hypothesis proposes that before DNA and proteins, RNA molecules performed both functions, both carrying information and catalyzing reactions, and that the more specialized DNA protein system we see in modern biology evolved later, from an earlier RNA-based chemistry. This hypothesis is compelling, but incomplete. Even granting that RNA can do both jobs, assembling the first self-replicating RNA molecule from scratch under early Earth conditions remains a chemistry problem that has not been fully solved. RNA is a complex molecule. Its spontaneous assembly from simpler components requires conditions that are specific and somewhat demanding. Researchers have made significant progress demonstrating plausible chemical pathways for the synthesis of RNA building blocks under conditions that could have existed on early Earth. But the complete, unbroken chain from simple chemistry to the first self-replicating molecule has not been demonstrated. The question of where is as unresolved as the question of how. Two environments dominate current research: hydrothermal vents, particularly the alkaline, lower temperature vents discovered more recently, which create natural proton gradients that may have driven the first energy-harvesting chemistry, offer a geologically stable, chemically rich environment where organic molecules could accumulate and react over long time scales. The concentration of reactants in the open ocean is generally too dilute for the necessary chemistry, but vent structures create microscopic pores and compartments that could have concentrated molecules effectively. The alternative is the warm little pond, tidal pools and shallow lakes on land, repeatedly wetted and dried by tidal cycles and evaporation. Concentration by evaporation is a powerful mechanism for driving chemistry that requires high local concentrations of reactants. Laboratory experiments have demonstrated that RNA building blocks can link into chains under repeated wet-dry cycles of the kind that shallow surface environments would have experienced on the early Earth. The Moon's enormous early tides, covering and uncovering tidal zones on cycles far more dramatic than those of the modern ocean, may have provided exactly this mechanism. The first living thing, whatever it was not complex. It was almost certainly simpler than the simplest organism alive today. Modern bacteria, the simplest free-living organisms, contain hundreds of genes and thousands of types of molecules, operating in a biochemical network of staggering intricacy. The first replicating system was almost certainly far more minimal. Perhaps a single self-replicating RNA molecule enclosed in a simple membrane made of fatty acids, the membrane providing a boundary between inside and outside, concentrating the chemistry, allowing the internal environment to be somewhat different from the external world, a bubble with chemistry inside it. That is perhaps all that was needed, in the right environment, with the right molecules, at the right concentration, a boundary, an inside, a chemistry that could copy itself imperfectly, producing variants, some of which copied themselves slightly better than others. The ones that copied better left more copies. The ones that copied less well left fewer. And in that simple, brutal logic, copy or don't, persist or don't, something that deserves the name natural selection began operating, before anything recognizable as an organism existed. Life did not begin as a cell. It began as a process of replication and variation and selection, operating on molecules in some sheltered corner of an early Earth that looked nothing like the world you know. And once that process started, it has not stopped. It has run continuously, without interruption, for 4 billion years, through every mass extinction, every ice age, every volcanic winter, every asteroid impact. The chain of replication has never fully broken. Every living thing on Earth today, from the bacteria in your gut to the largest blue whale, is part of an unbroken lineage of replication stretching back to that first molecule in that first warm, chemically rich environment. You are the latest iteration of a process that is 4 billion years old. The chemistry that became aware of itself has been running ever since, growing more complex, more varied, more capable of experiencing the world it exists in, until eventually it produced something that could lie still in the dark and contemplate its own origin, and find, at the bottom of that contemplation, not an answer, but a deeper and more beautiful question. How does matter learn to wonder about itself? We are still working on that one. Evolution. There is a process running on this planet that has no goal, no destination, no preference, no awareness of what it is producing or why. It does not try to make things better. It does not aim at complexity or intelligence or beauty. It has no concept of progress. It simply runs blindly, relentlessly, without pause or mercy, selecting for whatever happens to reproduce more successfully in whatever environment currently exists, discarding everything that doesn't, and repeating this process across billions of generations until the accumulated result looks, from the outside, like something that was designed. It was not designed. It is evolution, and it has been editing life on this planet for approximately 3.8 billion years. The mechanism is almost insultingly simple. Organisms reproduce. When they reproduce, they pass copies of their genetic information to their offspring. Those copies are not perfect. Errors occur during replication, producing mutations, small random changes in the genetic sequence. Most mutations are neutral. Some are harmful. They reduce the organism's ability to survive or reproduce, and organisms carrying them tend to leave fewer descendants. Some are beneficial. They improve survival or reproduction in some way, and organisms carrying them tend to leave more descendants. Over generations, beneficial mutations accumulate in a population. Harmful ones are weeded out. The population slowly changes, tracking whatever conditions currently favor survival and reproduction. That is the whole mechanism. Variation, inheritance, selection. 3 components. No foresight, no planning, no awareness of any kind. Just the differential reproduction of variance across deep time. And from that mechanism, over 3.8 billion years, emerged every living thing that has ever existed on Earth. The first life, those early self-replicating molecules in their fatty acid membranes, existed for hundreds of millions of years as something barely distinguishable from chemistry. Simple, small, metabolically minimal organisms, invisible to the naked eye, living in oceans that contained nothing more complex than themselves. For the first 2 billion years of life's history, evolution's entire output was microbial. Bacteria and archaea, single-celled organisms without a nucleus, were the only life on Earth for more than half of biology's total runtime. They were not simple, in any meaningful sense. The biochemical machinery inside even the most basic bacterium represents billions of years of evolutionary refinement, but they were, by the standards of what came later, uncomplicated. Then, approximately 2 billion years ago, something happened that remains one of the most consequential events in the history of life. One cell was engulfed by another and survived. The endosymbiotic theory, now broadly accepted, proposes that the complex cells of which all plants, animals, and fungi are made arose from a merger between simpler cells. A larger archaeal cell engulfed a smaller bacterial cell, and instead of digesting it, incorporated it as a permanent resident. That resident bacterium became the mitochondrion, the energy-producing organelle found in virtually every complex cell alive today. A similar event produced chloroplasts, the photosynthetic organelles in plant cells. The complex cell, the eukaryote, is a chimera, a merger, a collaboration between organisms that began as separate lineages. You are not descended from a single ancestral lineage. You are descended from a merger. The eukaryotic cell opened possibilities that prokaryotic cells had not exploited. More genetic material, more internal organization. The ability to develop into complex multicellular organisms, with cells specializing for different functions. A revolution in biological possibility that took another billion years to fully express itself. By approximately 600 million years ago, multicellular animals appeared, and the diversity of body plans that followed, in the Cambrian Explosion and beyond, represents evolution operating on a vastly expanded canvas. Evolution does not only produce gradual change. There are periods in the fossil record where change appears relatively slow and steady species persisting for millions of years with little modification, the population tracking a stable environment in which the current design works well enough, and there are periods of rapid change, evolutionary bursts triggered by new environments, new ecological opportunities, or the clearing of competitive space by mass extinction. The latter is particularly significant. Each mass extinction, while catastrophic in its destruction, opened ecological space that surviving lineages rapidly diversified to fill. The extinction of the non-avian dinosaurs 66 million years ago did not end life's story. It opened the chapter in which mammals previously small, nocturnal, ecologically marginal, diversified explosively into the ecological roles vacated by the dinosaurs. The mammals inherited a world cleared by catastrophe, and among those mammals, one particular lineage developed a characteristic that would prove, in evolutionary terms, extraordinarily consequential. Not strength, not speed, not size. A brain capable of learning, communicating, and accumulating knowledge across generations, not just within an individual lifetime, but culturally, socially, across time. This characteristic allowed a relatively weak, slow, physically unimpressive primate to outcompete almost every other large animal on the planet within an eye blink of geological time. Evolution produced intelligence, not because intelligence was the goal, but because, in the particular environment of the African savanna over the last several million years, intelligence happened to be extraordinarily good at surviving and reproducing. A brain capable of planning ahead, cooperating with others, using tools, and communicating complex information was selected for, not chosen, not designed, simply favored by the brutal arithmetic of differential reproduction. And once that brain crossed a certain threshold of complexity, it became capable of things evolution had no framework for predicting. It became capable of understanding evolution itself. This is perhaps the strangest thing the process has produced, a result of blind, goalless selection that can look back at the process that created it and describe it accurately. An outcome of 3.8 billion years of mechanical editing that can reconstruct the mechanism responsible for its own existence, life examining itself, the editing process reading its own manuscript. Evolution does not know you exist. It has no awareness of the thing it spent billions of years assembling. It will continue running after you, are gone, selecting, discarding, accumulating, editing, as indifferent to your absence as it was to your presence. The lineages that survive whatever comes next will not be chosen for their complexity or their intelligence or their capacity for wonder. They will simply be the ones that reproduce more successfully in whatever environment follows. The process does not care what it makes. It only cares if caring is even a word that applies that something keeps making more of itself. And for 3.8 billion years, something has. The Cambrian Explosion. For 3 billion years, life was invisible. Not rare, not struggling, invisible. Covering the floors of ancient oceans in vast microbial mats, drifting through the water column in uncountable billions, metabolizing and replicating and evolving with quiet, patient consistency, but producing nothing that left a clear impression in rock, nothing with hard parts to fossilize, nothing that would have been recognizable as animal life to eyes that had not yet evolved to see it. The first 3 billion years of life's history left almost no fossil record, not because nothing was happening, but because what was happening was soft-bodied, microscopic, and architecturally simple. Then, approximately 538 million years ago, something changed. In geological terms, it changed almost instantaneously. Over a period of roughly 20 million years, a blink. In the context of 3 billion years of prior biological history, the fossil record transforms from an almost empty canvas into something bewildering in its variety and complexity. Hard shells appear, mineralized skeletons, eyes, jointed limbs, predatory mouths, bodies organized along symmetrical plans. The basic anatomical blueprints, the body plans, of almost every major animal group alive on Earth today appear in the fossil record within this narrow window of time, many of them with no clear gradual precursor in the layers below. Paleontologists call it the Cambrian Explosion, and the name, for once, captures the reality. It was an explosion, an evolutionary detonation that produced more fundamental biological innovation in 20 million years than the preceding 3 billion had managed. Body plans that had never existed before appeared, diversified, competed, and either persisted or vanished in what amounts to evolution running at a rate that still challenges easy explanation. The Burgess Shale, discovered in the Canadian Rockies in 1909, and still among the most scientifically significant fossil deposits on Earth, preserves a snapshot of Cambrian life in extraordinary detail. Soft tissues, rarely preserved in the fossil record, are captured here in fine-grained sediment that buried organisms rapidly enough to prevent decomposition. What the Burgess Shale reveals is a world of extraordinary, sometimes bewildering diversity. Anomalocaris, a predator up to 1 meter long, with compound eyes and circular, grasping mouthparts, the apex predator of the Cambrian Ocean, more sophisticated than anything that had existed before it. Hallucigenia, a creature so strange that when first reconstructed, scientists placed it upside down, mistaking its legs for spines and its spines for legs. Opabenia, a soft-bodied organism with 5 eyes and a single flexible frontal appendage ending in a claw, belonging to no body plan that persists today. Euaxia armored with mineralized scales and spines, its feeding apparatus unlike anything in modern biology. Many of the body plans visible in the Cambrian have no living descendants. Entire branches of the tree of life, entire experiments in animal architecture appeared during the explosion, lived for millions of years, and went extinct without leaving any lineage in the modern world. The Cambrian was not just the origin of modern animal groups. It was a broader, wilder proliferation of biological possibility, most of which the universe tried and then discarded. What caused it remains one of paleontology's central questions. Several factors have been proposed, and most researchers believe the explosion resulted from multiple converging causes rather than a single trigger. The most compelling candidates include the following. Oxygen. The Great Oxidation event had occurred 2 billion years earlier, but oxygen levels continued rising gradually over geological time. By the Cambrian, atmospheric oxygen had reached levels sufficient to support the higher metabolic rates that active, motile, predatory animal life requires. Simple diffusion of oxygen through body tissues, adequate for flat, small organisms, becomes insufficient beyond a certain body size. Complex animals need circulatory systems to deliver oxygen to internal tissues, and those circulatory systems require oxygen concentrations that may not have been available earlier. The evolution of predation. There is a compelling argument that the Cambrian explosion was, at its core, an evolutionary arms race triggered by the appearance of the first active predators. Before predation, there was little evolutionary pressure to develop hard shells, eyes, speed, or complex sensory systems. The moment something began eating other things actively and selectively, every other organism in the ecosystem faced sudden, intense pressure to evolve defenses. Hard shells appeared within an evolutionarily short time of the first evidence of predation. Eyes, perhaps the most consequential innovation of the Cambrian, allowed organisms to detect predators and prey across distances, transforming the ecological dynamics of the ocean. The eye deserves particular attention. Eyes evolved independently dozens of times in different animal lineages, a phenomenon called convergent evolution, where different evolutionary paths arrive at the same solution to the same problem. The optical physics of image formation is the same regardless of which lineage is doing the solving, and evolution has discovered the camera-type eye, the compound eye, and several other designs multiple times in lineages as different from each other as vertebrates and cephalopods. The Cambrian Ocean appears to have been where eyes first became ecologically dominant, where the ability to see became a decisive competitive advantage that reshaped entire ecosystems around its consequences. A world that could not see became a world that could. And everything changed. There is also a geological factor worth considering. The Cambrian began shortly after the breakup of a supercontinent, which flooded vast areas of previously exposed rock under shallow tropical seas. Shallow marine environments, warm, sunlit, chemically rich, are among the most productive ecosystems on Earth. The creation of enormous shallow sea habitats may have opened ecological space that life rapidly diversified to fill, the physical geography of the planet handing evolution an opportunity it had not previously had. Whatever the cause, the result was irreversible. The Cambrian explosion established the ecological structure that has characterized animal life ever since. Predators and prey, competition and cooperation, the hierarchical food webs in which energy flows from photosynthetic producers through successive levels of consumers. The basic rules of ecological interaction that govern every ecosystem on Earth today were written in the Cambrian, in the soft-bodied, shelled, armored, eyed, jointed populations of a 500-million-year-old ocean. Your eyes, the ones moving behind closed lids as you drift towards sleep, are Cambrian technology. The basic architecture of your visual system, refined and elaborated over 500 million years of vertebrate evolution, traces its origins to the optical innovations of the Cambrian Explosion. The image-forming eye appeared in your lineage in that ancient ocean, in a world so unlike the present that you would not recognize a single species in it, among creatures so alien they were mistaken for hallucinations when scientists first tried to reconstruct them. Life spent 3 billion years invisible. Then, in 20 million years, it learned to see. And once it did, the world it saw was never the same again. Mass extinctions. Life on Earth has been almost completely destroyed at least 5 times, not damaged, not set back, almost completely destroyed. The living world, the accumulated product of hundreds of millions of years of evolution, the intricate web of species and ecosystems and biological relationships built up across deep time, has been reduced to a fraction of itself, repeatedly, by events so catastrophic that the word disaster fails to carry adequate weight. What we call mass extinctions are not simply periods of elevated species loss. They are collapses. They are moments when the biological complexity the planet had spent millions of years assembling was largely dismantled in what amounts, geologically, to an instant. And life survived all of them, not intact, not unchanged, not the same species, or the same ecosystems, or the same dominant groups, but the process, the continuous chain of replication and variation and selection never fully broke. Something always made it through, and whatever made it through inherited a world emptied of competitors, rich with ecological opportunity, and proceeded to diversify into the space that catastrophe had cleared. The history of life on Earth is not a story of steady progress interrupted by setbacks. It is a story written in catastrophes. The 5 major mass extinctions are recorded in the fossil record as sharp discontinuities layers of rock, where the diversity of species preserved below is dramatically greater than the diversity preserved above. The transition is sometimes visible in a single rock face, a few centimeters of sediment separating a world full of life from a world nearly empty of it. The oldest of the 5 major extinctions occurred at the end of the Ordovician period, approximately 445 million years ago. It eliminated roughly 85% of all species. The leading cause is believed to be a rapid glaciation event, the planet cooling dramatically as the supercontinent Gondwana drifted over the South Pole, triggering ice sheet expansion, dropping sea levels, and draining the shallow tropical seas that harbored the majority of Ordovician marine life. The cooling was followed by rapid warming as glaciation reversed, swinging ocean chemistry and temperature through changes too rapid for many species to adapt to. A 2-phase extinction, first the cold, then the rebound. The late Devonian extinction, approximately 375 million years ago, was not a single event, but a prolonged crisis lasting millions of years, during which marine diversity collapsed repeatedly across multiple pulses of extinction. The cause remains debated climate change, ocean anoxia, possibly the evolutionary appearance of land plants whose roots dramatically altered soil chemistry and runoff into the oceans, triggering algal blooms that depleted oxygen in shallow seas. The oceans lost an estimated 75% of their species. Reef ecosystems, some of the most diverse marine environments of the Devonian, collapsed almost entirely and did not fully recover for millions of years. Then came the worst. The Permian extinction, 252 million years ago, is the largest mass extinction in Earth's history. It eliminated approximately 96% of all marine species and 70% of terrestrial vertebrate species. It came so close to ending complex animal life on Earth that paleontologists sometimes call it the Great Dying. The cause primarily the Siberian Traps eruption, a massive volcanic episode that released enormous quantities of carbon dioxide, methane, and sulfur dioxide over approximately 1 million years, triggered a cascade of environmental disasters. Global temperatures rose by 10 degrees or more. The oceans acidified, depleting calcium carbonate and making shell formation impossible for vast numbers of marine organisms. Ocean oxygen levels plummeted, creating dead zones across enormous areas of the seafloor. The ozone layer was damaged by volcanic halogens, exposing the surface to elevated ultraviolet radiation, and acid rain, produced by sulfur dioxide emissions, may have devastated terrestrial plant communities. The Permian extinction did not happen quickly by human standards. It unfolded over thousands of years, long enough for each generation of organisms to experience a world slightly more hostile than the one their parents knew, but too fast for evolution to respond. The result was a world stripped of most of its complexity. Oceans nearly empty. Terrestrial ecosystems reduced to low-diversity communities dominated by a few hardy generalist species. Recovery took millions of years. The Triassic-Jurassic extinction, 201 million years ago, cleared the way for the dinosaurs. Prior to this event, the dominant large terrestrial animals were the cruratarsans, a group of archosaurs that outcompeted the early dinosaurs in most ecological roles. The extinction, again linked to massive volcanic activity, the Central Atlantic magmatic province erupting as Pangaea began to break apart, eliminated the Crurotarsans and opened the ecological stage for dinosaurian dominance. The dinosaurs did not rise because they were superior. They rose because their competitors were killed by a volcanic catastrophe. Dominance is often less about excellence than about survival of the catastrophe. The most famous extinction needs less introduction than the others. 66 million years ago, an asteroid approximately 12 kilometers in diameter struck the shallow seas of what is now the Yucatan Peninsula in Mexico at roughly 20 kilometers per second. The impact released energy equivalent to billions of nuclear weapons simultaneously. The explosion vaporized rock instantaneously. A fireball expanded outward. Ejecta were blasted into the upper atmosphere and rained back down globally, the kinetic energy of re-entry heating the atmosphere to temperatures sufficient to ignite wildfires across vast areas. The dust and soot injected into the stratosphere blocked sunlight globally for months to years, collapsing photosynthesis, destroying the plant base of terrestrial food webs. Global temperatures plummeted. The darkness and cold produced what is sometimes called an impact winter, a period of dramatically reduced sunlight and productivity that eliminated the large food webs that large animals depended on. Non-avian dinosaurs, which had dominated terrestrial ecosystems for 165 million years, were gone within what the geological record suggests was a geologically brief interval after the impact. The mammals that survived were small. They could survive on less food. They could shelter underground. They could eat almost anything. And they inherited a world from which the dominant vertebrates of the previous era had been erased. One of those small surviving mammals was the ancestor of every primate alive today. Including you, your existence is contingent on an asteroid impact 66 million years ago. If that asteroid had missed, if its trajectory had been slightly different, if it had arrived a few minutes earlier or later and struck deep ocean rather than shallow continental shelf, reducing the volume of vaporized sulfur-rich rock, the impact's severity might have been meaningfully reduced. The non-avian dinosaurs might have survived. The mammals might have remained small and ecologically marginal. The evolutionary path that led to primates, and from primates to hominids, and from hominids to modern humans, might never have opened. You are here because of a rock, and that rock arrived by chance. We are currently living through what many biologists describe as the sixth mass extinction, a global decline in biodiversity driven by habitat destruction, climate change, invasive species, and direct exploitation at rates that exceed the background extinction rate by factors of 100 to 1,000. Unlike the previous five, this one has an identifiable cause. It is not an asteroid or a supervolcano or a glaciation event. It is a single species, acting across the span of a few centuries, altering the planet's climate and consuming its ecosystems faster than most dinosaur species can adapt. The previous five extinctions were things that happened to life. This one is something life is doing to itself. Whether it will reach the scale of the previous five, and what will emerge from it if it does, depends on choices being made right now, in the brief geological instant we call the present, by the species that survived the last extinction, by being small enough and adaptable enough, and perhaps just lucky enough, to make it through. Life has survived everything the universe has thrown at it so far. It is less clear whether it has ever before had to survive itself. The rise of humans. 6 million years ago, In the forests and grasslands of Africa, a lineage of primates made a decision that was not a decision. No individual chose it. No group deliberated and voted. No conscious mind weighed the options and selected the path that would eventually produce civilization. A population of apes, in a particular region of a particular continent, in a particular climatic moment, began spending more time on the ground. Their posture shifted. Their gait changed. The skeletal architecture that had been optimized over millions of years for moving through trees began, slowly, across thousands of generations, to reorganize itself around walking upright on two legs. This was not inevitable. It was not the goal of evolution. It was a response to an environment, the African climate cooling and drying, forests retreating, grasslands expanding, and a particular lineage of primates finding that bipedalism, despite its costs, conferred enough advantages in the new open environment to be selected for: freed hands, the ability to carry food and infants while moving, better heat dissipation in open savanna conditions. Small advantages, compounding across vast time, producing a body plan that no primate had worn before. The first hominins were not impressive. Australopithecus, the genus that includes the famous fossil known as Lucy, discovered in Ethiopia in 1974 and dated to approximately 3.2 million years ago, was small-brained by modern standards, standing roughly a meter tall, walking upright, but retaining the long arms and curved fingers of a creature that still spent time in trees. The brain of Australopithecus was approximately 450 cubic centimeters, not dramatically larger than a chimpanzee's. If you had encountered one on the African savanna 3 million years ago, you would not have recognized it as the ancestor of anything particularly remarkable. What changed was the brain. Over the next 3 million years, in a process that is still not fully understood, the hominin brain grew. Not gradually and smoothly, but in periods of relatively rapid encephalization, punctuating longer periods of stability. By the time Homo erectus appeared, approximately 1.9 million years ago, brain volume had reached roughly 900 cubic centimeters. By the time Homo sapiens emerged, roughly 300,000 years ago, it had reached approximately 1,400 cubic centimeters, 3 times the volume of Australopithecus, produced in what amounts to an evolutionary sprint. Why the brain grew so fast, and what specifically drove the selection for larger brains, remains actively debated. The costs are clear. A large brain is metabolically expensive. The human brain, roughly 2% of body weight, consumes approximately 20% of the body's total energy budget. It requires a prolonged developmental period. Human infants are born helpless and require years of intensive care before reaching even basic independence, a vulnerability with no parallel among other primates. It necessitates a diet rich in high-quality nutrients. The expansion of meat consumption, likely enabled by the development of stone tool technology, may have been both a cause and a consequence of brain expansion, providing the caloric and nutritional density to sustain a larger brain, while the larger brain enabled more sophisticated hunting strategies. Social complexity is among the leading explanations. The social brain hypothesis proposes that the primary driver of hominin encephalization was not the physical environment, but the social environment, the cognitive demands of navigating complex social hierarchies, tracking relationships, modeling other individuals' intentions and knowledge, cooperating and competing within increasingly large and intricate social groups. A brain that could predict and manipulate the behavior of other members of its group had an enormous competitive advantage, and the cognitive arms race this created within hominin social groups may have driven rapid brain expansion in a self-reinforcing cycle. The intelligence that eventually produced art and language and science may have begun as a social manipulation tool. Stone tools appear in the archaeological record approximately 3.3 million years ago, older, remarkably, than the genus Homo, suggesting that tool use predates the lineage we tend to associate with technology. By 1.7 million years ago, Homo erectus was producing the Acheulean hand axe, a symmetrical, carefully shaped tool that required planning, manual dexterity, and the ability to visualize a three-dimensional form before it existed. The same basic tool design persisted, with relatively little modification, for over 1 million years, a consistency that suggests either cognitive limitation or a social transmission system stable enough to preserve a successful design across enormous spans of time. Fire changed everything. The controlled use of fire for warmth, protection, and cooking appears in the archaeological record with increasing confidence from approximately 1 million years ago, with possible evidence of earlier use stretching back further. Cooking is not merely a cultural practice, it is a biological transformation. Cooking breaks down cell walls, denatures proteins, gelatinizes starches, dramatically increasing the caloric and nutritional availability of food. A cooked diet extracts significantly more energy from the same quantity of food than a raw diet. The reduction in the time and energy required for digestion that cooking enabled may have contributed directly to the reduction of the human gut relative to other primates and the reallocation of metabolic resources to the brain. Fire also extended the usable day beyond sunset, creating hours of social time, protected from predators, around a light source. Those hours may have been where language deepened, where stories were first told, where the accumulated knowledge of a group was transmitted across generations in something approaching a cultural archive. Homo sapiens appeared in Africa approximately 300,000 years ago. For the first 100,000 years or more, there is little archaeological evidence of the behavioral modernity that would later define the species. The transition to what archaeologists call behaviorally modern humans, characterized by symbolic art, complex tools, long-distance trade networks, personal ornamentation, and evidence of abstract thought, appears more clearly in the record from approximately 100,000 years ago onward, with a particular flowering of symbolic and technological complexity beginning around 50,000 years ago. What triggered this behavioral revolution is debated. Some researchers point to a genetic change, a mutation affecting brain organization or language capacity that crossed a threshold of cognitive possibility. Others argue the change was not biological, but cultural. A critical mass of population density and social connectivity that allowed innovations to accumulate and spread faster than they were lost, producing a ratchet effect where cultural complexity built on itself. The difference matters. One implies a single biological event. The other implies a social and demographic threshold that, once crossed, became self-sustaining. Homo sapiens was not the only hominin alive at this time. Neanderthals, a separate hominin species that had evolved in Europe and Western Asia over hundreds of thousands of years, were present across a wide range when modern humans began expanding out of Africa approximately 70,000 years ago. Neanderthals were not primitive. They had large brains, in some cases larger than the modern human average. They made tools. They buried their dead, suggesting some concept of mortality and perhaps ritual. They created personal ornaments. They may have spoken. and when modern humans arrived in their territory, the two species coexisted and, in some regions, interbred, a fact confirmed by the discovery that most people outside of sub-Saharan Africa carry 1 to 4% Neanderthal DNA in their genome. The Neanderthals are gone, whether they were outcompeted, absorbed through interbreeding, or eliminated by some combination of factors, including the climate disruption that followed a massive volcanic eruption approximately 39,000 years ago, remains debated. What is clear is that within a few thousand years of modern human arrival in any given region, the other hominin species in that region disappeared. This pattern, modern humans expanding into new territory, and the previous inhabitants vanishing, repeated in Europe, in Asia, and eventually across the globe. Modern humans reached Australia approximately 65,000 years ago. The megafauna are the giant wombats, the marsupial lions, the diprotodons weighing 3 tons went extinct shortly after. Modern humans reached the Americas approximately 15 to 20,000 years ago. The mammoths, the mastodons, the ground sloths, the American horses, the giant beavers gone within millennia of human arrival. Modern humans reached the islands of the Pacific over the last few thousand years. The giant birds, the endemic mammals, the naive fauna that had evolved without terrestrial predators gone. This pattern is too consistent to be coincidence. Wherever modern humans arrived, the largest animals in the ecosystem, the megafauna, declined or vanished. The hunting pressure of a species with projectile weapons, cooperative hunting strategies, and the ability to use fire to drive and trap animals applied to fauna that had not evolved alongside a hunting pressure of that sophistication was in many cases simply too much. Humans were not the most physically imposing predator, not the fastest, not the strongest, not equipped with the most impressive natural weapons. But humans could plan, could communicate, could coordinate complex behavior across large groups, could teach strategies to offspring and pass knowledge across generations without biological inheritance. The apex predator of planet Earth is not the one with the sharpest claws. It is the one with the most elaborate internal model of the world it inhabits. And in 10,000 years, from the first agricultural settlements to the global civilization that now shapes the chemistry of the atmosphere and the composition of the biosphere, that apex predator has transformed the planet more completely than any single species in the history of complex life, with the possible exception of the cyanobacteria that first oxygenated the atmosphere 2.5 billion years ago, an accidental product of a retreating forest and a changing climate, 6 million years ago, on one continent, of one planet, orbiting one star. That is what you are. That is what built the world you are lying in right now. And it is still not entirely clear whether the thing that made us so successful is going to be enough to help us survive what our success has produced. Consciousness. There is something it is like to be you. That sentence sounds simple. It sounds almost redundant. Of course, there is something it is like to be you. You are experiencing it right now. The particular texture of this moment. The weight of your body against the surface beneath you. The sound of these words forming meaning somewhere behind your eyes. The subtle background hum of existing that has been present every moment of your waking life and that you have almost certainly never stopped to examine, because it is so constant, so total, so thoroughly the medium you swim in, that noticing it feels like a fish noticing water. But that sentence, there is something it is like to be you, is one of the most philosophically loaded statements in the history of human thought. Because we do not know why it is true, We can describe the brain in extraordinary detail. We can map the neurons, roughly 86 billion of them in the human brain, each connected to thousands of others, forming a network of approximately 100 trillion synaptic connections. We can observe which regions activate during different experiences. We can trace the electrochemical signals that propagate through neural tissue when you see a color or feel pain or recognize a face. We can describe the architecture of the visual cortex, the function of the hippocampus in memory formation, the role of the prefrontal cortex in planning and decision-making. Neuroscience has produced a detailed, increasingly precise map of the brain's physical operations. What neuroscience cannot yet explain is why any of that produces experience. Why the electrochemical signals in your visual cortex, when light of a particular wavelength strikes your retina, produce not just a neural response, but the felt quality of redness, the subjective experience of seeing red, which is something entirely different from a wavelength measurement, and which cannot be inferred from any physical description of the brain process alone. This gap between the objective physical description and the subjective felt experience is what philosopher David Chalmers called the hard problem of consciousness, and it remains, despite decades of intense interdisciplinary research, genuinely unsolved. The easy problems of consciousness are not easy in any ordinary sense. They include explaining attention, memory, learning, sleep, the integration of information from different sensory sources, the difference between waking and unconscious states. These are extraordinarily complex scientific questions that have occupied researchers for generations, but they are, in principle, tractable. They ask how the brain performs certain functions, and the answer, however difficult to obtain, is in principle a mechanistic one. The hard problem is different in kind. It asks not how the brain processes information, but why that processing is accompanied by experience at all. Why there is something it is like rather than nothing. There is no agreed answer. The dominant framework in neuroscience is some version of physicalism. The view that consciousness is a product of physical brain processes, that subjective experience arises from neural activity in a way that will eventually be explained by a sufficiently complete neuroscience. The details of how exactly this works, which neural processes give rise to consciousness, what the sufficient conditions are deeply contested. Global workspace theory proposes that consciousness arises when information is broadcast widely across the brain, becoming available to multiple cognitive systems simultaneously. Integrated information theory proposes that consciousness is identical to a particular kind of information integration, measurable in principle in any physical system, biological or otherwise. Higher-order theories propose that conscious states are mental states that are represented by higher-order mental states, that you are conscious of something when you are, in some sense, aware of being aware of it. Each framework has evidence in its favor. Each has serious objections, and none of them fully dissolves the hard problem. There are more radical proposals. Panpsychism. The view that consciousness or proto-conscious properties are fundamental features of reality, present in some form in all matter, and that human consciousness is a complex organization of these fundamental properties rather than something that emerges entirely from non-conscious components, has attracted serious philosophical attention in recent years, not because it is unproblematic, but because the alternatives seem equally problematic. If consciousness cannot emerge from non-conscious matter, perhaps consciousness was never entirely absent from matter in the first place. This is not a fringe position. It is a serious philosophical proposal taken seriously by serious thinkers. And it raises a question that is difficult to dismiss. If consciousness is a fundamental feature of the universe rather than an emergent product of sufficiently complex biology, then the universe has not produced consciousness, it has always contained it, in forms too simple to recognize as such, organizing over billions of years into the complex, self-aware arrangements we call minds. The universe would not merely have produced something capable of looking at itself. It would have always been looking, in some minimal sense, and only recently developed eyes complex enough to notice. Consider what consciousness has made possible. Every piece of knowledge accumulated in this script, the Big Bang, the first stars, dark matter, black holes, the origin of life, the history of evolution exists because conscious minds observed the universe, formed hypotheses about it, tested those hypotheses against reality, and communicated the results across generations. The universe's self-knowledge, its capacity to understand its own structure and history, is entirely mediated by consciousness. Without it, the cosmos would continue to exist and operate according to its laws, but it would do so in total ignorance of itself. Stars would live and die without being named. Galaxies would collide without being observed. The entire 14-billion-year history reconstructed in this series of reflections would have happened in complete darkness, not physical darkness, but epistemic darkness. The darkness of a universe with no interior, no perspective, no awareness of its own existence. Consciousness is what gives the universe an inside, and we do not know where that inside comes from. The philosophical stakes here are not merely academic. The question of what consciousness is determines the question of what you are. If consciousness is purely physical, a product of particular neural arrangements, then it can, in principle, be replicated, transferred, or produced in non-biological systems. If it is something more fundamental, something not fully captured by any physical description, then the implications are different and stranger. The question of whether other animals are conscious, and to what degree, changes how we understand our moral obligations to them. The question of whether future artificial systems could be conscious changes how we understand the nature of the minds we might be building. These questions are not settled. They may not be settled in your lifetime. You are, right now, a conscious entity lying in the dark, aware of being aware, experiencing the experience of existing, unable to fully explain how or why any of that is happening, using a brain that evolved for survival on an African savanna, to contemplate mysteries that savanna survival required no capacity to address. The universe spent 14 billion years producing a mind capable of asking why it exists. It has not yet provided the answer. And perhaps the most quietly unsettling possibility is this, that consciousness, the thing you are most certain of, the one fact of your existence that is more immediate and undeniable than any external observation you have ever made, is also the thing about which the least is understood. You know that you experience. You do not know what experience is, and neither does anyone else. Time. You cannot stop it. You cannot slow it. You cannot reverse it. You cannot step outside of it and look at it from a neutral position, because there is no position outside of it. Everything that exists inside time, carried forward by it, at a rate you have no control over, toward a future you cannot see, away from a past you cannot return to. Time is the one thing every conscious being has in common, the one dimension of reality that no living thing has ever escaped, even briefly. The current you're swimming in, right now, in this moment, that has been carrying you forward since before you were aware of being carried. and that will continue carrying whatever remains of you long after awareness stops. What is strange is that physics barely understands it. At the level of fundamental physics, at the level of the equations that govern the behavior of particles and fields, time is almost irrelevant. The laws of physics, at the microscopic level, are time-symmetric. The equations work equally well, run forward or backward. If you filmed a collision between two elementary particles and played the film in reverse, the reversed version would be indistinguishable from a real physical event. The laws of physics, as written, do not strongly prefer one direction of time over the other. And yet the universe has a direction. The past is fixed. The future is open. You remember yesterday and not tomorrow. Heat flows from hot objects to cold ones, never spontaneously the reverse. Eggs break and do not unbreak. Stars burn and do not unburn. Every process you have ever observed in the macroscopic world has a preferred direction, a before and an after, that are not interchangeable. This directionality, the arrow of time, is not written clearly into the fundamental laws. It emerges from something else. That something else is entropy. The second law of thermodynamics states that the total entropy of a closed system tends to increase over time. Entropy, loosely, is a measure of disorder, the number of microscopic arrangements that correspond to a given macroscopic state. A cup of hot coffee cooling in a room is not violating any law of physics at the microscopic level. The individual molecular collisions are all perfectly time-reversible, but the macroscopic process is overwhelmingly likely to run in one direction, because there are vastly more microscopic arrangements corresponding to the coffee and room being at the same temperature than to the coffee being hot and the room being cool. Disorder increases not because physics demands it, but because disorder is simply more probable than order, and probability wins over time. The arrow of time is, in this view, a statistical phenomenon. The past feels fixed because entropy was lower in the past. There were fewer microstates, more order, more usable energy. The future feels open because there are more high-entropy arrangements for the universe to explore than low-entropy ones, and it is exploring them continuously. Memory works in one direction because recording information, storing a stable representation of a past state, requires increasing entropy. Your brain forms memories by making physical changes to neural tissue, changes that are themselves increases in entropy. You remember the past and not the future, not because of something metaphysical about the nature of time, but because of the thermodynamic directionality of information storage. But this explanation raises a deeper question. Why was entropy low to begin with? If the universe tends toward higher entropy, if disorder is the overwhelmingly probable state, why did the universe start in a state of extraordinarily low entropy, the highly ordered, dense, hot singularity of the Big Bang? This is what physicist Roger Penrose has called the problem of the specialness of the Big Bang. The initial state of the universe was so improbably ordered, so remarkably low in entropy, that explaining why it started that way is one of the deepest unsolved problems in cosmology. The arrow of time, the entire structure of before and after, past and future, cause and effect, traces back to this initial condition. We experience time as flowing because the universe began in an improbably ordered state and has been exploring less ordered configuration ever since. Einstein's relativity added another layer of strangeness. In Newtonian physics, time was absolute, a universal clock, ticking at the same rate everywhere, the same for all observers. Einstein showed this was wrong. Time is relative, It passes at different rates depending on your velocity and your position in a gravitational field. A clock moving at high speed ticks more slowly than a stationary one-time dilation. A clock deep in a gravitational well closer to a massive object ticks more slowly than one far from gravitational time dilation. These are not theoretical curiosities. They are real, measurable effects. The GPS satellites orbiting Earth move at high speed and experience weaker gravity than clocks on the surface. Without corrections for both special and general relativistic time dilation, GPS systems would accumulate errors of kilometers per day. Your phone knows where you are, in part, because engineers accounted for the fact that time passes slightly differently in orbit than on the ground. The more extreme the conditions, the more dramatic the effect. Near the event horizon of a black hole, time dilation becomes extreme. An observer falling toward a black hole would experience time passing normally from their own perspective, while an outside observer would see that infalling observer's clock appearing to slow to a halt as they approached the horizon. From the outside, they would never appear to cross it, frozen at the boundary, for as long as the universe exists. From the inside, they cross it in finite personal time and continue inward towards the singularity. Time, near extreme gravity, does something that has no analogue in ordinary human experience. There is a more fundamental question lurking beneath all of this. Does time actually flow? Our experience of time, the sense that the present moment is moving, that now is special, that there is a felt passage from past to future, is one of the most basic features of conscious experience. It feels as though time is dynamic, that moments succeed each other, that the present is perpetually arriving and the past is perpetually receding. But in the physics of relativity, there is no preferred present. All moments exist equally in the four-dimensional space-time. Block past, present, and future are all equally real, equally existent, laid out in a structure that does not flow or change. The sense that time passes, in this view, is a feature of consciousness rather than of physics, an artifact of the way minds experience a static space-time structure from within. This view, sometimes called the block universe or eternalism, implies that every moment of your past still exists somewhere in the structure of space-time, that every moment of your future also already exists, equally fixed, equally real, that the you who existed 10 years ago is not gone, but simply located at a different coordinate in a four-dimensional manifold, that the you who will exist 10 years from now, if you will exist, is equally real right now, simply inaccessible from your current position. The present is not special in this picture. It only feels special because you are inside it. Perhaps the deepest thing that can be said about time is this. It is the dimension that makes narrative possible. Without time, there is no before or after, no cause or effect. No story, only a static structure of simultaneous facts with no order among them. Every story ever told, every history, every explanation, every scientific theory is a story about time, about how one thing led to another, about sequences and consequences and the irreversible accumulation of change. The universe's story, the one this script has been slowly telling, is entirely a story about time. The Big Bang happened. Then the first stars ignited. Then galaxies formed. Then planets condensed. Then chemistry became biology. Then biology became aware of itself. Each then is a marker on the timeline, an arrow pointing in one direction only, from lower entropy to higher, from simpler to more complex, from the extraordinarily ordered initial conditions of the universe toward whatever it is becoming. You are a product of that arrow. Your consciousness, your awareness of this moment, your memory of the past, your anticipation of the future, exists because the universe had a beginning and has been moving away from it ever since. Time is the river. You are what the river made. And the river has never, in 14 billion years, reversed its course. Nothing in the universe moves faster than light. Not as a practical limitation, not the way a car is limited by its engine or a runner is limited by their muscles. As a fundamental, absolute constraint written into the structure of space-time itself. The speed of light in a vacuum, approximately 300,000 kilometers per second, is not a speed that light happens to travel at. It is the speed limit of the universe, the maximum velocity at which any information, any signal, any physical influence of any kind can propagate through space. Nothing with mass can reach it. Nothing without mass can travel slower. It is, in a very precise sense, the speed of causality, the rate at which one event can influence another. And it is still not fast enough to make the universe feel small. Light crosses the diameter of the Earth in roughly a 20th of a second. It travels from the Earth to the Moon in about 1.3 seconds. From the Earth to the Sun, 8 minutes. From the Sun to the edge of the solar system, to the point where the solar wind gives way to interstellar space, roughly 16 hours. These are the distances that feel large to human beings. These are the scales of the solar system, the neighborhood, the local environment, and light crosses them in hours. Then the distances stop being manageable. From the solar system to the nearest star, Proxima Centauri, light takes 4.2 years. Not 4.2 hours. Not 4.2 days. 4.2 years, traveling at 300,000 kilometers per second, the fastest anything can move, without pause or deceleration, to reach the next nearest point of light in a universe containing 2 trillion galaxies. The Milky Way is 100,000 light-years across. The Andromeda Galaxy, the nearest large galaxy, is 2.5 million light-years away. The observable universe extends approximately 46 billion light-years in every direction. The speed of light, the fastest speed possible, applied continuously for the entire age of the universe, does not get you across the observable universe. Because the universe has been expanding during the time the light has been traveling, regions that emitted the oldest light we can detect have since moved far beyond the distance that light has traveled. The observable universe is larger than the light traveled distance from its edge because space itself expanded while the light was crossing it. Light is the fastest thing, and the universe is so large that it still fails to cross it. What light is, at a fundamental level, took centuries to work out. For most of human history, the nature of light was simply assumed rather than investigated. Newton believed light was a stream of particles, corpuscles, traveling in straight lines, reflecting and refracting according to mechanical rules. His contemporary Huygens argued light was a wave, propagating through space like a ripple on water. The debate persisted for over a century, with evidence accumulating on both sides, until the 19th century, when James Clerk Maxwell's equations of electromagnetism predicted the existence of electromagnetic waves traveling at a speed that matched the measured speed of light, revealing that light was an electromagnetic wave, a self-propagating oscillation of electric and magnetic fields requiring no medium to travel through. This was revolutionary, and it created a problem. Every wave that had ever been studied, sound, water, seismic waves, required a medium, a material that was doing the waving. What was doing the waving in the case of light? physicists postulated a medium they called the luminiferous ether, an invisible, all-pervading substance filling the universe through which electromagnetic waves propagated. In 1887, Albert Michelson and Edward Morley designed an extraordinarily precise experiment to detect Earth's motion through the ether by measuring variations in the speed of light in different directions. They found none. The speed of light was the same in every direction, regardless of Earth's motion. The ether did not exist. Light needed no medium, and the speed of light appeared to be constant, independent of the motion of the source or the observer. This result was so strange, so incompatible with classical mechanics, that it took Einstein's special theory of relativity in 1905 to make sense of it. Einstein's insight was to take the constancy of the speed of light seriously as a fundamental postulate and work out what the rest of physics must look like if it were true. The result was a complete restructuring of the concepts of space and time. If the speed of light is constant for all observers, regardless of their motion, then different observers moving relative to each other must experience time and space differently. Time dilation, length contraction, the relativity of simultaneity. Two events that are simultaneous for one observer may not be simultaneous for another. The geometry of space-time is not the rigid, absolute structure Newton assumed, but a flexible, observer-dependent fabric shaped by motion and gravity. All of this follows from the speed of light being constant. But light is also a particle. This was Einstein's other major contribution of 1905, the photoelectric effect, for which he actually received the Nobel Prize. When light strikes certain metals, it ejects electrons, but only if the light is above a certain frequency, regardless of intensity. This cannot be explained if light is purely a wave. Einstein proposed that light comes in discrete packets of energy photons, each carrying an energy proportional to its frequency. The photoelectric effect is explained immediately if light is made of particles. But the wave experiment's interference, diffraction, require light to be a wave. Both descriptions are correct. Light is neither purely a wave nor purely a particle. It is a quantum object, exhibiting wave-like behavior in some experimental contexts and particle-like behavior in others, with no single classical description adequate to capture both. This wave-particle duality is not a limitation of our understanding, but a genuine feature of quantum reality. Light is what it is, and what it is does not fit neatly into categories derived from the macroscopic world. When you look at the night sky, you are looking into the past. Every photon reaching your eye left its source at some point in the past and has been traveling toward you at the maximum speed the universe permits ever since. The moon, you see, is the moon as it was 1.3 seconds ago, the sun 8 minutes ago, the nearest star 4.2 years ago, the Andromeda Galaxy, that faint smear of light visible to the naked eye on a clear night, as it was 2.5 million years ago, before anatomically modern humans existed. The most distant objects visible to the naked eye are billions of light-years away. The light reaching your eyes from them began its journey before the Earth existed. The night sky is not a view of the universe as it is. It is a view of the universe as it was, at different moments, layered on top of each other, a temporal collage assembled by the finite speed of light, showing you the past at different depths simultaneously. When astronomers observe the most distant galaxies, the ones at the edge of the observable universe, seen as they were when the universe was only a few 100 million years old, they are not observing the distant universe. They are observing the early universe. Distance and time are the same thing at cosmological scales. The deeper you look into space, the further back in time you see, because light takes time to travel, and time is the thing that light cannot outrun. The speed of light is a window and a wall simultaneously. A window because it allows information to travel, allows the distant universe to communicate its existence to us through the photons it emits. A wall because it limits what we can ever know. Regions beyond the observable horizon are permanently inaccessible, their light never reaching us, because the expansion of space carries them away faster than light can cross the gap. Everything you have ever seen, every face, every landscape, every star you saw in the past. The present is invisible. By the time light from anything reaches your eyes, time has passed. The present moment, the actual current state of anything you observe, is always slightly behind the image arriving at your retina. For objects close by, the delay is imperceptible. For the stars, it is years or centuries or millennia. For the distant galaxies, it is billions of years. You have never seen the universe as it is, only as it was. And the light carrying that ancient image has been traveling toward you at the maximum speed anything can travel, for longer than you will ever be able to fully comprehend. Gravity. Of all the forces that govern the universe, gravity is the weakest. Not slightly weaker, not modestly weaker, incomparably, almost absurdly weaker than the other fundamental forces of nature. The electromagnetic force is roughly 10 to the power of 36 times stronger than gravity. That is a 1 followed by 36 zeros. The strong nuclear force, which holds atomic nuclei together, is even stronger still. Gravity is so weak at the scale of fundamental particles that it is essentially irrelevant to particle physics. The gravitational attraction between two protons is so negligible compared to the electromagnetic repulsion between them that physicists routinely ignore gravity entirely when calculating the behavior of subatomic systems. And yet gravity runs the universe, not because it is strong, because it is cumulative, universal, and infinite in range. Every other force has limitations. The strong nuclear force operates only within the nucleus, beyond a few femtometers. It simply does not exist. The electromagnetic force, while long-range, can be shielded. Positive and negative charges cancel each other out, and matter in bulk is electrically neutral, so large objects do not generally exert significant electromagnetic forces on each other. Gravity has no such limitations. It cannot be shielded. It cannot be neutralized. Every piece of mass and energy in the universe attracts every other piece of mass and energy across any distance, without exception, without cancellation, without end. Add enough matter together, and the weakness becomes irrelevant. Planets, stars, galaxies, galaxy clusters at these scales, gravity dominates everything. It shapes the large-scale structure of the universe. It determines the life cycles of stars. It governs the orbits of planets. It pulls matter into the dense configurations where nuclear fusion can ignite. Without gravity, the Big Bang's expanding cloud of gas would have remained a uniform, featureless fog forever. No stars, no planets, no chemistry, no life. Gravity is the architect, the force that took a smooth, cooling universe and pulled it into the intricate, structured, luminous cosmos that exists today. For most of human history, gravity was understood as a force. Newton's formulation, published in 1687 in the Principia Mathematica, described gravity as an attractive force between masses, acting instantaneously across any distance, proportional to the product of the masses and inversely proportional to the square of the distance between them. It was extraordinarily successful. It predicted the motion of planets with remarkable accuracy. It explained the tides, the trajectories of comets, the behavior of pendulums. For over 2 centuries, Newtonian gravity was one of the most precisely verified theories in all of science. It was also wrong, not wrong in the sense of being useless. Newtonian gravity remains accurate enough for most practical purposes and is still used to calculate spacecraft trajectories today. But wrong in the sense of being an incomplete description of what gravity actually is. The problem was action at a distance, the idea that 2 masses could exert forces on each other instantaneously across empty space, with nothing mediating the interaction. Newton himself found this troubling. In a letter, he wrote that the idea of one body acting on another at a distance through a vacuum, without any mediation, was so great an absurdity that he believed no man of philosophical sense would ever fall into it. He could describe gravity with precision. He could not explain what it was. Einstein could. In 1915, Einstein published the general theory of relativity, which replaced the concept of gravitational force entirely with a geometrical description. Gravity, in Einstein's framework, is not a force at all. It is the curvature of space-time, produced by mass and energy. Matter tells space-time how to curve. Curved space-time tells matter how to move. What we experience as the gravitational pull of the Earth is not a force pushing us towards the ground. It is the curvature of space-time in the vicinity of the Earth's mass, causing objects to follow the straightest possible paths through that curved geometry, paths that happen to lead towards the Earth's surface. The Earth is not pulling you down. Space-time is curved beneath you, and you are following the curve. This reframing produced predictions that Newtonian gravity could not: the bending of light around massive objects, gravitational lensing, because light follows the curvature of space-time as surely as matter does. The precession of Mercury's orbit, a tiny discrepancy from Newtonian predictions that had puzzled astronomers for decades, explained precisely by general relativity. The gravitational redshift of light photons losing energy as they climb out of a gravitational well, their frequency shifting toward the red end of the spectrum. Gravitational time dilation clocks running slower in stronger gravitational fields, a consequence of the geometry of space-time near massive objects. All of these were confirmed by observation and experiment. And in 2015, exactly 100 years after Einstein published General Relativity, the Laser Interferometer Gravitational Wave Observatory LIGO detected gravitational waves for the first time. Gravitational waves are ripples in the fabric of space-time itself, produced when massive objects accelerate most dramatically when massive objects merge. The event detected in 2015 was the merger of 2 black holes, each roughly 30 times the mass of the Sun, spiraling toward each other over billions of years, their final merger releasing more energy in a fraction of a second than all the stars in the observable universe emit, combined. Radiated almost entirely as gravitational waves, ripples spreading outward through space-time at the speed of light, diminishing as they traveled, reaching Earth 1.3 billion years later as a distortion of space-time so small that it moved the mirrors of LIGO's 4-kilometer-long detector by a distance 1/10,000th the diameter of a proton. That signal was detected. The precision required to detect it, a displacement smaller than any previously measured in human history, filtered from the background vibrations of traffic and ocean waves, and the thermal motion of atoms in the detector's mirrors, represents perhaps the most remarkable measurement ever made by human technology. And it confirmed, directly, that space-time is a physical medium that can bend, stretch, ripple, and carry waves. Gravity is the universe talking to itself through the geometry of space and time. Yet gravity remains, in a profound sense, the most mysterious of forces. Every other fundamental force has been successfully incorporated into the framework of quantum mechanics, described in terms of quantum fields and force-carrying particles. The electromagnetic force is mediated by photons, the strong force by gluons, the weak force by W and Z bosons. Gravity has no such description. Every attempt to quantize gravity to build a quantum theory of gravity compatible with general relativity has so far failed to produce a complete, consistent framework. String theory and loop quantum gravity are the leading candidates, but neither has produced testable predictions confirmed by experiment. Gravity and quantum mechanics are the two most successful theories in the history of physics. They are fundamentally incompatible with each other. At the scales where quantum effects matter inside black holes, at the moment of the Big Bang, both theories are needed simultaneously, and they produce contradictions. The reconciliation of gravity with quantum mechanics is perhaps the deepest open problem in theoretical physics. Its solution, when and if it comes, will likely require a revision of our most basic concepts of space, time, and matter, as fundamental as the revision Einstein made to Newton. Gravity shaped the universe from the first fraction of a second after the Big Bang. It collapsed the first gas clouds into the first stars. It pulled stars into galaxies and galaxies into clusters. It bent the path of light across cosmological distances. It curved the orbit of the planet you live on into a stable loop around the sun. It holds the atmosphere against the surface. It keeps the oceans from drifting into space. It pulls the rain from clouds to the ground. It keeps your body pressed against the surface you are lying on right now. It is the weakest force in the universe, and it is the reason anything in the universe looks the way it does. The loneliest force, infinite in reach, unable to be shielded or neutralized, acting on everything, always, from everywhere, has spent 14 billion years quietly assembling the cosmos out of the raw material the Big Bang provided. It is still working. Right now, as you lie still, gravity is pulling everything toward everything else. Patiently, without pause, without end. Quantum mechanics. There is a version of reality operating beneath the one you experience. Not metaphorically beneath, not philosophically beneath, in the sense of being more fundamental in some abstract way. Physically beneath at scales smaller than atoms, smaller than the nuclei of atoms, smaller than the particles that make up those nuclei. There is a layer of reality governed by rules so different from the ones that operate at human scales that every analogy eventually breaks down, every intuition eventually fails, and every attempt to visualize what is actually happening produces a picture that cannot be correct. This is not a failure of human imagination that a sufficiently clever analogy could fix. It is a feature of the territory. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions have been confirmed to an accuracy of 1 part in 10 billion, the equivalent of predicting the distance from New York to Los Angeles to within the width of a human hair. It is the foundation of everything, from the transistors in every computing device to the laser in every barcode scanner, to the MRI machines that image the interior of the human body. The technology of the modern world runs on quantum mechanics. Its practical success is beyond dispute, and nobody fully understands what it is saying about the nature of reality. Begin with the wave function. In quantum mechanics, a particle, an electron, a photon, any quantum object, is not described by a definite position and a definite velocity, the way a baseball or a planet is. It is described by a wave function, a mathematical object that encodes, for every possible position and state, a probability amplitude. The wave function does not say where the particle is. It says where the particle might be found if you look, and with what probability. Before measurement, the particle does not have a definite position. It exists in a superposition, a combination of multiple possible states simultaneously, each with an associated probability. When you measure it, the superposition collapses. The particle is found at a specific location. The probability wave collapses to a definite outcome, and this transition from a spread-out superposition of possibilities to a single definite result is called wave function collapse, and it is one of the most philosophically contested processes in all of physics. The mathematics of quantum mechanics describes the wave function evolving smoothly and deterministically according to the Schrödinger equation right up until measurement, at which point something discontinuous happens. The superposition collapses, one outcome is selected, and the other possibilities vanish. What causes this collapse? What counts as a measurement? Why does the definite world of our experience emerge from the indefinite quantum world beneath it? Nobody agrees. These questions are not about the math. The math works. These questions are about what the math means, about what is actually happening in reality when a quantum system evolves and is measured. The various answers on offer are called interpretations of quantum mechanics, and they disagree with each other so fundamentally that choosing between them requires philosophical commitments that physics alone cannot settle. The Copenhagen interpretation, the oldest and still widely taught, says the wave function is not a description of physical reality, but a tool for calculating probabilities. There is no deeper story about what the particle was doing before measurement. Asking where it was before you looked is simply not a meaningful question. The quantum world is irreducibly probabilistic, and the collapse upon measurement is just the updating of our knowledge, not a physical event. This interpretation sidesteps the hard questions by declaring them unanswerable. The many worlds interpretation, proposed by Hugh Everett in 1957, takes the opposite approach. It says the wave function never collapses. The Schrödinger equation always applies. When a measurement occurs and the wave function appears to collapse to one outcome, what actually happens is that the universe branches. Every possible outcome occurs, each in a different branch of a vast, continuously expanding tree of parallel realities. In one branch, the particle was here. In another, it was there. Both are equally real. The observer in each branch experiences only their own outcome and has no access to the others. If many worlds is correct, the universe is almost incomprehensibly larger than it appears as an ever-branching structure of parallel histories, each as real as the one you inhabit, collectively containing every outcome of every quantum event that has ever occurred since the beginning of time. There are other interpretations. Pilot wave theory, which restores determinism by positing a hidden wave guiding particles along definite trajectories. Relational quantum mechanics, which holds that quantum states are not absolute, but relative to the observer. Cubism, which treats the wave function as an agent's personal probability assignment rather than an objective feature of reality. Each resolves some problems and creates others. None commands consensus. The most famous illustration of quantum strangeness is the double-slit experiment. Fire electrons one at a time at a barrier with two slits, and detect where each electron lands on a screen behind the barrier. Classical intuition says each electron goes through one slit or the other and lands in one of two clusters behind each slit. What actually happens is different. The electrons build up an interference pattern, alternating bands of high and low detection, probability identical to the pattern produced by waves passing through two slits and interfering with each other. Each individual electron, fired alone, contributes to an interference pattern that could only arise if the electron passed through both slits simultaneously, interfering with itself. Now close one slit. The interference pattern disappears. The electrons behave like particles again. Now leave both slits open, but place a detector at one slit to determine which slit each electron passes through. The interference pattern disappears again. The act of measuring which path the electron took, of gaining information about its trajectory, eliminates the interference. The electron stops behaving like a wave and starts behaving like a particle, simply because someone checked. The measurement changes the outcome. The act of observation is not passive. It participates in creating the reality it observes. This is not a statement about the limitations of experimental technique about disturbing the system by looking at it. It is a fundamental feature of quantum reality. The information gained by a measurement, the correlations established between the quantum system and the measuring device, is what eliminates the interference. Reality at the quantum level is not pre-existing and independent, waiting to be discovered. It is, in some sense, brought into definiteness by interaction. Entanglement takes this further. Two particles can be prepared in an entangled state, a shared quantum state that cannot be decomposed into independent descriptions of the two particles separately. When one entangled particle is measured and its state determined, the state of the other is instantly correlated, regardless of the distance between them. Einstein called this spooky action at a distance and believed it demonstrated that quantum mechanics was incomplete, that there must be hidden variables, pre-existing properties carried by the particles that determined their outcomes before measurement, eliminating the apparent non-locality. In 1964, physicist John Bell derived a mathematical inequality that could distinguish between quantum mechanics and any hidden variable theory. Experiments, particularly those of Alain Aspect in the 1980s, and numerous increasingly refined experiments since have consistently violated Bell's inequality, confirming quantum mechanical predictions and ruling out local hidden variable theories. The correlations between entangled particles are real. They are not explained by pre-existing properties, and they appear instantaneously regardless of separation. This does not allow faster-than-light communication. The correlations are only apparent when the results from both measurements are compared through classical channels. But it does mean the universe is non-local in a precise technical sense, that entangled particles share a connection that transcends the spatial separation between them, that the universe cannot be fully described as a collection of locally independent parts. The quantum world is not a smaller, simpler version of the everyday world. It is a different kind of thing, entirely probabilistic, where classical physics is deterministic, non-local, where classical physics respects locality, observer-dependent, where classical physics assumes an objective, pre-existing reality. And it is not confined to some remote, microscopic realm, with no implications for the large-scale world. Quantum mechanics underlies the stability of atoms, the chemistry of molecules, the operation of the sun's fusion reactions, the behavior of semiconductors, the folding of proteins. The everyday world is quantum mechanical at its foundation. The classical world you experience is an emergent approximation, valid at the scales your senses evolved to navigate, built on a substrate that operates by rules your intuition was never equipped to grasp. You are made of particles that do not have definite positions until they interact, held together by forces mediated by particles that exist as probability waves until they are exchanged, kept stable by the same quantum rules that prevent electrons from collapsing into nuclei, a prohibition with no classical explanation, arising purely from the quantum mechanical constraint that no two identical fermions can occupy the same state, a rule called the Pauli exclusion principle that is ultimately why matter is solid, why chemistry exists, why atoms have the structures they do, why you are not a puddle of undifferentiated particles on the floor. The universe you touch and see and lie inside is made of something you cannot picture, and the best description of that, something that human intelligence has ever produced, quantum mechanics, precise to 1 part in 10 billion, still leaves the question of what is actually happening entirely open. Reality is stranger than you are allowed to think, because thinking uses a brain built for a world that is itself only an approximation, and the approximation, however useful, does not reach all the way down. The multiverse. What if this is not the only universe? Not as a thought experiment, not as a metaphor, as a genuine scientific possibility, one that emerges not from speculation or philosophy, but from the mathematics of our best physical theories, appearing uninvited in the equations, demanding to be taken seriously by physicists who would, in many cases, prefer it weren't there. The multiverse is not one idea. It is several distinct ideas, arising from different areas of physics, each with its own mechanism, its own implications, its own particular flavor of reality-expanding strangeness. And they cannot all be dismissed. Begin with the one that follows most directly from ideas already covered in this series. Cosmic inflation, the theory that the universe underwent a period of exponentially accelerating expansion in the first fraction of a second after the Big Bang was developed in the early 1980s to solve several problems with the standard Big Bang model. It explains why the universe is so geometrically flat. It explains why the cosmic microwave background is so uniform in temperature across regions of the sky that, without inflation, could never have been in causal contact. Inflation is not fringe science. It is a central part of modern cosmology, supported by multiple lines of observational evidence. But inflation has a consequence that its originators found uncomfortable. In most models of inflation, the exponential expansion does not end everywhere simultaneously. Quantum fluctuations cause inflation to end in some regions while continuing in others. The regions where inflation ends become bubble universes, regions of space with their own physical properties, their own post-inflation evolution, potentially their own physical constants. Meanwhile, the space between these bubbles continues inflating, spawning more bubbles, endlessly. This is eternal inflation. And if eternal inflation is correct, our observable universe, everything within the 46 billion light-year sphere we can detect, is one bubble in an infinite sea of bubbles, each a universe unto itself, separated from all others by eternally inflating space that nothing can cross. These other universes are not hypothetical in the sense of being invented to explain something. They are a prediction, an unwanted but apparently unavoidable consequence of the mathematics of inflation. If you accept inflation, and the observational evidence strongly supports it, eternal inflation follows from most inflationary models with an almost irresistible logical momentum. The second source of multiverse thinking comes from quantum mechanics. The many-worlds interpretation discussed in the previous section proposes that the wave function never collapses. Every quantum event that could have multiple outcomes produces all of them, each in a separate branch of a continuously expanding tree of parallel realities. In this picture, the multiverse is not spatially separate universes beyond an unreachable boundary. It is a branching structure of parallel histories, each as physically real as the one you inhabit, each containing observers who experience their branch as the one and only reality. every quantum event generates branches. And quantum events are happening continuously, at every scale, in every cubic centimeter of the universe, at every moment. The number of branches, the number of parallel realities being generated, is not merely large. It is, in any meaningful sense, infinite. And in those branches, every quantum outcome that could have occurred does occur. Every radioactive atom that could have decayed at a different time decays at that different time in its own branch. Every photon that could have taken a different path takes that path somewhere. Every biological mutation that could have happened differently in some branch, with consequences that ramify forward through evolutionary time. Every decision you have ever made that felt genuinely uncertain, every fork in the road where you could have gone either way, may have spawned branches in which you went the other way. This is not poetry. It is the literal implication of the mathematics, if the many worlds interpretation is correct. The third flavor of multiverse arises from string theory. String theory, which will be explored in more detail in the next section, predicts the existence of extraspatial dimensions beyond the three we experience, and allows for an enormous number of possible vacuum states, different configurations of those extra dimensions that produce universes with different physical constants, different particle masses, different forces. The number of possible string theory vacua is estimated at something like 10 to the power of 500, a number so incomprehensibly large it has no useful analogy in ordinary experience. Each vacuum corresponds to a universe with its own physical laws. This collection of possible universes is called the string theory landscape. And here is why it matters in a way that goes beyond abstract mathematics. The physical constants of our universe, the strength of gravity, the mass of the electron, the cosmological constant that governs the expansion rate, appear to be extraordinarily finely tuned for the existence of complex structures. Small changes to many of these constants would produce a universe in which stars cannot form, or atoms are unstable, or the universe expands too fast for matter to clump together. The universe we inhabit seems, suspiciously, almost designed to permit the existence of complexity. There are two ways to explain this apparent fine-tuning. One is that there is a designer that the constants were set deliberately by something outside the universe, choosing values compatible with life. The other is that there are vastly many universes with different constants, and we inevitably find ourselves in one compatible with our existence because we could not exist in any other. This second explanation is called the anthropic principle. It requires no designer, only a large enough ensemble of universes with varying constants, and the simple observation that we can only observe a universe that permits observers. The multiverse in this context is not merely a philosophical curiosity. It is a proposed explanation for why the universe looks the way it does. But here is the problem that haunts all multiverse theories, and it is a serious one. The other universes, whether the bubble universes of eternal inflation, the branches of many worlds, or the landscape of string theory are, by definition, either causally disconnected from ours or inaccessible in ways that make direct observation impossible. We cannot send a signal to a parallel universe. We cannot receive one. We cannot perform an experiment that detects another branch or another bubble. The multiverse makes predictions about our universe. It explains the fine-tuning. It produces specific patterns in the cosmic microwave background that might be detectable as signatures of bubble collisions, but the other universes themselves remain permanently beyond the reach of observation. This troubles many physicists. Science is built on testability, a theory that cannot, even in principle, produce observable predictions that could distinguish it from alternatives, is by some definitions not a scientific theory at all. Critics of multiverse theories argue that they are metaphysics dressed in mathematical clothing, not wrong necessarily, but not science in any traditional sense. Proponents argue that the multiverse is a prediction of theories that do make testable predictions, and that dismissing it requires arbitrary methodological restrictions, that if the mathematics of well-supported theories points toward other universes, intellectual honesty requires taking that seriously, even if direct observation is impossible. The debate is genuine, unresolved, and touches on the deepest questions about what science is and what it is for. What is not in doubt is the scale of the implication. If any version of the multiverse is correct, the universe we can observe the 46 billion light-year sphere of 2 trillion galaxies that constitutes the entirety of our observational horizon is not the universe. It is a region, a pocket, a single instance of something that may exist in unimaginable numbers of instances, each slightly or dramatically different, each real in whatever sense this one is real, each containing or not containing the conditions for something like awareness, something like life, something like the particular improbable chain of events that produced you in this branch, in this bubble, in this configuration of an almost incomprehensibly large physical reality. You may be one of an infinite number of versions of yourself, each living out a different branch of the quantum tree, each convinced with complete justification that their branch is the one that actually happened, each lying in the dark right now, in a universe that may or may not be alone. The heat death of the universe. Everything ends. Not as metaphor, not as philosophy, as physics. The universe, for all its scale and complexity and improbable beauty, is subject to the same thermodynamic laws that govern the cooling of a cup of coffee or the running down of a battery. Energy flows from concentrated states to dispersed ones. Order gives way to disorder. The arrow of time points in one direction only, and at the end of that arrow, further away than any distance yet discussed in this series, further away than the death of the last star, further away than the evaporation of the last black hole, there is a state that physicists call heat death, and it is the most complete silence the universe will ever know. To understand where everything is going, it helps to understand where everything is now. The universe today is approximately 13.8 billion years old. It is in what cosmologists consider a relatively early and active phase of its existence. Stars are still forming. Galaxies are still colliding and merging. Black holes are still growing. The cosmic web of filaments and voids is still evolving. The universe is bright, energetic, structured, a place where complexity can exist because usable energy is still flowing from concentrated sources to dispersed sinks, and life and chemistry and thought can hitch a ride on that flow. This phase will not last. Star formation, the process by which gas clouds collapse under gravity and ignite nuclear fusion, depends on the availability of cold, dense gas. Dark energy is accelerating the expansion of the universe, gradually pulling matter apart, reducing the density of gas available for star formation. The rate of star formation in the universe has already peaked. It was highest approximately 10 billion years ago and has been declining since. Over the next trillion years or so, the remaining gas in galaxies will gradually be consumed by star formation, and the last stars will ignite and burn out without replacement. The era of stars will end. The last stars to die will be the smallest red dwarf stars, tiny, dim, extraordinarily fuel-efficient, burning their hydrogen so slowly that some will persist for 10 trillion years. 10 trillion years. The current age of the universe is less than 14 billion years. The longest-lived red dwarfs will outlast the current age of the universe by a factor of roughly 1,000. But even they will eventually exhaust their fuel, cool, and fade to darkness. When the last star goes out, the universe will enter a period sometimes called the degenerate era. The remaining matter will be locked in objects that no longer generate light through fusion white dwarfs, the cooling remnants of sun-like stars, neutron stars, the dense remnants of more massive stars, black holes, and cold, dark planetary bodies that never ignited. These objects will persist for an almost unimaginable span of time, slowly cooling, radiating their stored heat into an increasingly cold and empty cosmos. White dwarfs, cut off from any energy source, will cool over quadrillions of years into objects called black dwarfs. Cold, dark, inert spheres of crystallized carbon and oxygen, as massive as stars, invisible in the dark. No black dwarf is believed to exist yet. The universe is not old enough. The time required for a white dwarf to cool to the temperature of the surrounding space itself, dropping toward absolute zero as the universe expands and the cosmic microwave background radiation redshifts toward nothing, is longer than the current age of the universe by many orders of magnitude. The first black dwarfs will not form for longer than any timescale yet discussed. They represent the fate of ordinary matter on a timescale so vast that the numbers lose their meaning as numbers and become simply symbols for incomprehensibility. Then there are the black holes. Black holes will outlast every other structure in the universe. Even as stars die and galaxies darken and white dwarfs cool to black, the supermassive black holes at the centers of galaxies will persist growing, if anything, as they swallow the remaining matter in their vicinity. But even black holes are not permanent. As discussed in the section on black holes, Hawking radiation, the slow quantum mechanical evaporation of black holes through the emission of thermal radiation, causes black holes to lose mass over time. The process is extraordinarily slow. A stellar mass black hole takes longer to evaporate via Hawking radiation than the current age of the universe raised to a very high power. A supermassive black hole, millions or billions of times the mass of the Sun, takes longer still. But the process is inexorable. Given sufficient time, every black hole evaporates. The largest black holes in the observable universe will evaporate in approximately 10 to the power of 100 years. That number, a googol years, is so far beyond any human timescale that comparing it to the age of the universe is like comparing the age of the universe to a single Planck time, the smallest meaningful unit of time in physics. It is not a number that corresponds to any human experience of quantity. It is simply a symbol for an almost theological remoteness in time, but it ends. In a brief burst of Hawking radiation, a final flash of high-energy photons, as the last black hole's mass crosses below a critical threshold and the evaporation accelerates, the last black hole disappears. And what remains is a universe containing nothing but the products of black hole evaporation. A thin, cold, extraordinarily diffuse gas of photons and other particles spread across a space so vast that the probability of any two particles ever interacting again is negligible. The universe reaches thermal equilibrium, every region of space at the same temperature. No gradients of temperature or energy remaining, no flow of energy from one place to another, no work being done, no process occurring that is distinguishable from the passage of time. The universe is not destroyed, it is not collapsed or compressed or obliterated. It continues to exist. It simply reaches a state from which no further change is possible, a state of maximum entropy, minimum usable energy, and perfect, featureless, eternal sameness. This is heat death. Not hot. The temperature will be indistinguishable from absolute zero. The name refers not to heat in the sense of warmth, but to thermodynamic heat, the concept that when all energy has fully dispersed and equilibrium has been reached, no further work can be extracted from any temperature difference, because no temperature differences remain. The universe will not die in fire. It will die in the most complete stillness imaginable. No light, no warmth, no structure, no process. No time, in any meaningful sense, because time as we experience it requires change, and change requires an arrow of entropy, and entropy will have reached its maximum and stopped increasing. The universe will not be dark the way a room is dark when you turn off the light. It will be dark the way nothing is dark. The absence of any physical process that could produce a signal or receive one, or be affected by one. And yet, even at the theoretical end of everything, quantum mechanics inserts a strange and almost poetic footnote. In a universe at maximum entropy, quantum fluctuations still occur. The vacuum is never truly static, and given infinite time, or something approaching it, sufficiently large quantum fluctuations can spontaneously produce ordered structures out of the thermal noise. Given long enough, a fluctuation could produce, by pure chance, a single organized conscious mind, a brain, or something like a brain, with memories that did not correspond to any real history, flickering into existence for a moment from the background noise before dissolving again. These hypothetical entities are called Boltzmann brains, named after the physicist Ludwig Boltzmann, who first considered the thermodynamic implications that lead to this possibility. They are almost certainly not real. Most physicists believe the probability of a Boltzmann brain forming is so vanishingly small that even across infinite time, the implications are more of a philosophical curiosity than a physical prediction. But the fact that the mathematics of thermodynamics even produces this possibility, that even at the theoretical end of the universe, in the deepest silence, after the last black hole has evaporated and the last photon has redshifted to nothing, there might still occasionally be, by pure chance, a moment of awareness arising from the noise is something worth holding quietly. The universe might end not in total oblivion, but in the rarest, most isolated flickers of accidental experience. Minds without history, without context, without any way to know that everything that came before them, the Big Bang, the first stars, the galaxies, the planets, the oceans, the billions of years of life evolving toward complexity, the civilizations that rose and fell on a small rocky world orbiting an ordinary star, happened at all. Everything you are, and everything that made you, would be as inaccessible to them as the heat death is to you. The universe began in a moment of extraordinary order. It will end in a stillness so complete that nothing will remain to remember it ever burned. The observable universe. There is a wall around you. Not a physical wall, nothing you could touch or see or detect with any instrument directly, but a boundary, real and absolute, beyond which nothing can ever reach you, and from which you can never receive any signal of any kind. A sphere, centered precisely on your position, that defines the totality of everything you can ever know about the universe through direct observation. Not the totality of everything that exists, the totality of everything that can ever, even in principle, be known to exist from where you stand. Beyond that boundary, the universe continues. It almost certainly continues for an enormous distance, possibly infinitely. Other galaxies, other stars, other planets, other chemistry, other histories playing out in complete isolation from ours, separated not by space alone, but by the fundamental physics of light and causality. We cannot see them. We cannot detect them. We cannot communicate with them or receive communications from them. They are as effectively non-existent, from our observational perspective, as if they were not there at all. And they are almost certainly there. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends approximately 46 billion light-years in every direction. The universe is 13.8 billion years old, so light has been traveling for 13.8 billion years. How, then, is the observable universe 46 billion light-years across rather than 27.6 billion? Because space itself has been expanding during the time the light was traveling. The most distant light we can detect was emitted when the universe was very young, from regions that were then much closer. Those regions have since been carried away by the expansion of space to distances far beyond where the light originated. The observable universe is not a fixed object. It is a moving window, defined by our position in time as much as in space. Every second that passes, light from slightly more distant regions reaches us for the first time regions whose light has been traveling since slightly earlier in the universe's history, whose existence we were previously unaware of. In this sense, the observable universe grows. New information arrives continuously, from deeper and deeper in space and time, as the light from increasingly remote sources completes its journey. But it also shrinks, in a more fundamental sense. Dark energy is accelerating the expansion of space. Distant galaxies are receding faster and faster. There is a distance called the Hubble horizon, beyond which galaxies are already receding faster than light. Not because they are moving through space faster than light, which is prohibited, but because the space between us and them is expanding faster than light can cross it. Light from those galaxies, already in transit toward us, will never arrive. The space it must cross is expanding faster than it can travel. Those galaxies are already beyond any hope of direct observation, even though their light has been streaming toward us. The number of galaxies inside our observable universe is approximately 2 trillion. The number outside it, in the unobservable regions of a universe that may be infinite, is if the universe is indeed infinite, also infinite. There may be infinitely more universe beyond our horizon than within it. The 2 trillion galaxies we can observe may be an arbitrarily small fraction of everything that exists, and we have no way of knowing. By definition, we cannot observe what lies beyond the observational horizon. We can infer it exists. The physics that operates inside our horizon gives no reason to expect it stops at the boundary, but we cannot measure it, map it, or characterize it directly. We live inside a cosmic bubble of knowability, and the bubble has a surface we can never reach. The cosmic microwave background, the oldest light in the observable universe, emitted approximately 380,000 years after the Big Bang, when the universe first became transparent, marks the effective visual edge of the observable universe. It is light from the moment when photons first decoupled from matter and were free to travel through space. Looking at it is looking back as far as electromagnetic radiation can take us to a time when the universe was a hot, dense plasma, before any stars or galaxies had formed. Beyond it, in the sense of earlier times, the universe was opaque to light. We cannot see further with photons. Gravitational waves potentially offer a different window. Gravitational waves, unlike light, are not blocked by the opaque early universe. They propagate freely through matter, through plasma, through the conditions of the very early universe. Detecting primordial gravitational waves, ripples from the first moments after the Big Bang, potentially even from the inflationary epoch, would extend our observational reach backward in time, beyond what light allows. This is an active area of research, with space-based gravitational wave detectors planned that could, in principle, detect such signals. But even gravitational waves cannot take us beyond the observable universe in the spatial sense. The horizon is not a feature of our instruments. It is a feature of causality itself. Nothing travels faster than light. Therefore, no information from beyond the horizon can reach us. The boundary is not an engineering problem that better telescopes will solve. It is a fundamental limit on what physics allows us to know about the cosmos from our particular position in space and time. Consider what this means for the question of cosmic loneliness. If other civilizations exist in the universe, and the sheer number of galaxies and stars and potentially habitable planets makes their existence feel plausible to many astronomers. Some of them are almost certainly beyond our observable horizon, not merely far away in the sense of being unreachable with current technology, far away in the sense of being permanently, fundamentally beyond any possible communication, regardless of the technology that might be developed in any future. The expansion of space will never allow a signal to cross the growing distance. Civilizations that exist beyond our horizon are as isolated from us as if they existed in a separate universe. The observable universe is not the universe. It is our universe, the portion that causality has allowed to touch us, bounded by the speed of light and the age of time, defined by our position in an expanding cosmos. Another observer, located in a galaxy 100 billion light-years away, has their own observable universe, a sphere centered on them, overlapping with ours in the regions between us, extending beyond ours in the directions away from us, containing galaxies and structures we will never see. Every point in the universe is the center of its own observable universe. Every observer is surrounded by their own unique sphere of knowability, their own wall beyond which information cannot travel. There is no privileged position, no cosmic center from which the whole can be observed, no vantage point from which everything is visible. The universe, at its largest scales, is a collection of overlapping but individually bounded perspectives, each real, each complete in itself, each permanently ignorant of what lies beyond its own horizon. You are, right now, at the center of your observable universe. Not because you are special, not because the cosmos arranged itself around you, but because the observable universe is always centered on the observer, wherever they are, because light travels outward in all directions equally, and the horizon is equally distant in every direction from every point. You are the center of a sphere 46 billion light-years across. Beyond that sphere, the universe continues vast, possibly infinite, certainly unknowable in its full extent, and the wall that separates the knowable from the unknowable is not made of anything. It is made of time and the speed of light and the expansion of space, the most fundamental features of the universe pressing against the boundaries of what any mind, anywhere, can ever learn. The universe is not hiding what lies beyond the horizon. It is simply larger than knowing, and it always will be. Cosmic inflation. In the first fraction of a second after the Big Bang, something happened that makes every other event in the history of the universe look slow. Not slightly faster, not dramatically faster, incomparably, almost definitionally faster. A period of expansion so extreme that the universe grew from something smaller than a subatomic particle to something roughly the size of a grapefruit in approximately 10 to the power of -32 seconds. That is a decimal point, followed by 31 zeros and then a 1. A unit of time so small it has no analogue in human experience, no comparison that does it justice, a duration so brief that calling it an instant fails to capture how much smaller than an instant it actually was. In that non-time, the universe expanded by a factor of at least 10 to the power of 26. And it did so faster than light. This requires immediate clarification, because it appears to contradict everything established in the section on light, the universal speed limit, the maximum velocity of anything in the universe. The clarification is this: the speed of light limits the motion of objects through space. It does not limit the expansion of space itself. Space is not a thing moving through something else. It is the something else, the fabric in which everything is embedded. And the expansion of that fabric has no speed limit. During inflation, space itself was stretching so rapidly that points within it were being carried apart faster than light could travel between them. Nothing moved faster than light. Space simply grew faster than light could cross it. This distinction is real and important. It is the same mechanism responsible for the cosmic horizon discussed in the previous section. The reason some regions of the universe are already beyond the reach of any signal we could ever send, not because they moved away faster than light, but because the space between us and them expanded faster than light. Inflation took this process and ran it at an inconceivable rate for a brief, crucial window of time in the universe's earliest moments. The theory of cosmic inflation was proposed in 1980 by physicist Alan Guth. He was not looking for inflation specifically. He was trying to solve 3 problems with the standard Big Bang model problems that the model's mathematics produced, but could not resolve internally. The first was the flatness problem. The universe's geometrically flat space, on large scales, behaves according to Euclidean geometry, rather than curving positively like the surface of a sphere, or negatively like a saddle. For the universe to be as flat as we observe it, its initial conditions would have to be fine-tuned to an extraordinary degree. A density so precisely calibrated to the critical density that any significant deviation would have caused the universe to recollapse long ago or expand so fast that matter never clumped together. The flatness requires explanation. The second was the horizon problem. The cosmic microwave background, the oldest light in the observable universe, is extraordinarily uniform in temperature. Every direction you look, it is the same temperature to roughly 1 part in 100,000. But regions of the sky that are separated by more than a few degrees were, in the standard Big Bang model, without inflation, causally disconnected at the time the background radiation was emitted. They had never been in contact. Light had not had time to travel between them. There was no physical mechanism by which they could have reached the same temperature, and yet they are the same temperature. The horizon problem asks, how? The third was the magnetic monopole problem. Grand unified theories of physics attempts to unify the strong, weak, and electromagnetic forces into a single framework predict the existence of exotic particles called magnetic monopoles, which should have been produced in enormous quantities in the hot early universe. We have never detected a single one. Inflation solves all 3 problems simultaneously. if the very early universe underwent a period of exponential expansion, then the observable universe we see today, the entire 46 billion light-year sphere, originated from a region so small that it was causally connected before inflation began. Every part of it had time to reach thermal equilibrium before being stretched to cosmic scales, explaining the uniformity of the microwave background. The exponential expansion also stretched the geometry of space so aggressively that any curvature present before inflation was smoothed to imperceptibility, the way the surface of a balloon appears flat when the balloon is inflated to enormous size. And the dilution produced by inflation was so extreme that any monopoles produced before or during inflation were spread across a volume so vast that the expected number within our observable universe is effectively zero. One mechanism, three solutions. The driving force behind inflation is hypothesized to be a field called the inflaton field, permeating space in its earliest moments, existing in a high-energy false vacuum state that generated a kind of repulsive gravity, an enormous outward pressure that drove the exponential expansion. As the inflaton field rolled down toward its true vacuum, its lowest energy state inflation slowed and ended. The energy of the field converting into the hot plasma of particles and radiation that populated the universe at the beginning of the conventional Big Bang epoch. The end of inflation is sometimes called reheating, the moment when the energy driving the expansion was transferred into the matter and radiation that would eventually form everything in the observable universe. The quantum fluctuations in the inflaton field during this period are not a minor detail. They are the origin of everything. Quantum mechanics ensures that no field can be perfectly smooth. There are unavoidable quantum fluctuations, tiny variations in the field's energy from place to place. During inflation, these microscopic quantum fluctuations were stretched by the exponential expansion to macroscopic scales, imprinted on the distribution of matter and energy as the expansion ended. These density variations regions, slightly more dense and slightly less dense than the average, became the seeds of all large-scale structure. The slight overdensities attracted more matter through gravity, grew over billions of years into the filaments and clusters of the cosmic web, eventually forming the galaxies and stars and planets that populate the observable universe today. You exist because of quantum fluctuations that occurred in the first fraction of a second after the Big Bang, stretched to cosmic scales by inflation. The particular arrangement of matter in the observable universe, the specific locations of galaxies, the particular cluster in which the Milky Way sits, the specific nebula from which the solar system condensed, traces back to random quantum noise in the earliest moments of time, magnified by inflation into the blueprint from which everything was built. The evidence for inflation is substantial but not yet conclusive. The pattern of temperature fluctuations in the cosmic microwave background, measured with extraordinary precision by satellites, including WMAP and Planck, matches the predictions of inflationary models with remarkable accuracy. The spectrum of fluctuations, their statistical properties, the specific pattern of acoustic peaks in the background radiation all are consistent with inflation having occurred. But the smoking gun evidence would be the detection of primordial gravitational waves ripples in space-time produced by the violent exponential expansion itself, imprinted on the polarization of the cosmic microwave background in a specific pattern called B-mode polarization. This signal has not yet been definitively detected. Several experiments are searching for it. Ground-based arrays in Antarctica and Chile proposed space missions. If found, it would not only confirm inflation, but constrain which specific inflationary model is correct, providing a direct observational window into physics at energies that no particle accelerator will ever reach. A window into the first fraction of a second of the universe's existence, opened not by building larger instruments, but by reading the faint polarization signature in light that has been traveling since before the first atom existed. Inflation also leads, as discussed in the section on the multiverse, to eternal inflation, the possibility that the exponential expansion never entirely stopped, that it continues in regions beyond our horizon, spawning bubble universes in an endless cascade. If eternal inflation is correct, then the observable universe is not merely a small fraction of the total universe. It is an incomprehensibly small fraction of an infinite structure, a single bubble in an ocean of eternally inflating space, its physical constants and initial conditions determined by the particular way inflation ended here. The universe we know is a bubble, formed when a quantum field, in the first unimaginably brief moments of time, rolled from one energy state to another in our particular region of an inflating cosmos. Everything in this bubble, every star, every planet, every ocean, every living thing, every thought that has ever been thought, is the consequence of that transition. The heat and energy released when inflation ended became the matter and radiation of the Big Bang. The quantum fluctuations, stretched by the expansion, became the seeds of structure. The geometry, flattened by the expansion, became the space-time in which gravity could do its patient work over billions of years. A quantum field, transitioning between energy states in a fraction of a second, so brief it has no name in ordinary language. That is what made everything. That is what made you. And there is something almost impossible to hold in the mind about the fact that the universe we know, with all its complexity, its 14 billion years of history, its 2 trillion galaxies, its one confirmed instance of life and awareness, began as a quantum fluctuation in a field that no longer exists, in a moment so brief it defies description, in the first heartbeat of a cosmos that did not yet know it would become anything at all. String theory. Every particle you have ever heard of is, according to string theory, the same thing vibrating differently. Not similar things, not analogous things, the same thing. A single fundamental object, a tiny, one-dimensional loop or strand of energy, so small that if an atom were scaled to the size of the solar system, a string would be roughly the size of a tree, vibrating at different frequencies, in different patterns, producing what appears at larger scales as different particles with different properties. The electron is a string vibrating one way. The quark is a string vibrating another way. The photon, the gluon, the neutrino, all strings, all the same fundamental object, all distinguished only by the mode of their vibration. In this picture, the universe is not made of things. It is made of music, or something so mathematically analogous to music that the metaphor is less poetic license and more genuine structural description. Different notes on a string produce different sounds. Different vibrational modes of a fundamental string produce different particles. The entire particle content of the universe, everything in the standard model of particle physics, and more, emerges from the harmonic spectrum of a single type of object. This is the central claim of string theory, and it is simultaneously one of the most beautiful and one of the most frustrating ideas in the history of physics. Beautiful because it offers something physics has wanted for a century, a unified description of all fundamental physics. The standard model of particle physics, for all its extraordinary success, is a patchwork. It describes 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force, within the framework of quantum field theory, with each force mediated by its own set of quantum particles, but gravity sits outside it, described by general relativity, a fundamentally different kind of theory that resists incorporation into the quantum framework. The Standard Model has 19 free parameters, numbers like particle masses and coupling constants that the theory requires as inputs but does not explain. It works with remarkable precision, but it is not a complete or satisfying picture of reality at its deepest level. String theory, almost accidentally, contains gravity. When physicists first developed string theory in the late 1960s and 1970s, they were trying to describe the strong nuclear force, not gravity. The theory kept producing a massless spin-2 particle, an unwanted result that seemed to have no place in nuclear physics. When it was recognized that a massless spin-2 particle is precisely what a quantum theory of gravity would require the hypothetical graviton, the perspective shifted entirely. String theory was not a failed theory of the strong force. It was a potential theory of everything. A quantum theory of gravity, the missing piece that has eluded physics for a century. This is why string theory attracted and continues to attract some of the most mathematically gifted physicists in the world. Not because it has been confirmed experimentally, it has not, but because it is the most mathematically consistent framework that naturally incorporates both quantum mechanics and gravity without the contradictions that destroy every other attempt at unification. The mathematical coherence of string theory, its internal consistency, its ability to produce results that surprise its developers and reveal unexpected connections between seemingly unrelated areas of physics. These are, for its proponents, evidence that the theory is tracking something real, but consistency is not confirmation. String theory requires extra dimensions, not metaphorical dimensions, not dimensions in some abstract mathematical sense detached from physical reality. Actual spatial dimensions beyond the three we experience, in which the strings themselves exist and vibrate. The mathematics of string theory works is internally consistent without producing nonsensical infinities only in 10 or 11 dimensions of space-time, depending on the version. Since we observe only 3 spatial dimensions and 1 time dimension, the extra 6 or 7 dimensions must, if string theory is correct, be curled up on themselves compactified at scales so small that no current or foreseeable experiment could directly detect them. The size of the extra dimensions in the most common string theory models is comparable to the string scale itself, approximately the Planck length, roughly 10 to the power of -35 meters. This is 17 orders of magnitude smaller than the diameter of a proton. No instrument remotely approaches the resolution needed to probe these scales directly. The extra dimensions are, for all practical experimental purposes, invisible. The shape of the extra dimensions matters enormously. The particular way the extra dimensions are curled up, their topology, their geometry determines the physical properties of the observable universe. Different compactification geometries produce different particle masses, different force strengths, different physical constants. The space of possible compactifications, called the string theory landscape, contains an estimated 10 to the power of 500 distinct possibilities, each corresponding to a universe with different laws of physics. This number 10 to the 500 is both the theory's most impressive feature and its most serious problem. Impressive because it provides, through the anthropic principle, a potential explanation for the apparent fine-tuning of the universe's physical constants. If there are 10 to the 500 possible universes with different constants, and we inhabit one compatible with our existence, no further explanation of the fine-tuning is needed. We are simply in the compatible one. The vast landscape of possibilities is not a weakness of the theory. It is the mechanism that explains why the constants are what they are without requiring a designer. Problematic because a theory that predicts 10 to the 500 possible universes is, in the view of many physicists, not making a prediction at all. If almost any set of physical constants is realizable somewhere in the landscape, and we observe the constants we observe simply because they are compatible with our existence, then string theory cannot be falsified by any measurement of physical constants. The landscape absorbs any result. Whatever we measure, some region of the landscape produces it. A theory that cannot be falsified, that is consistent with any possible observation, is by the traditional standards of scientific method, not a scientific theory. This criticism is serious, and string theorists take it seriously. The response, generally, is that string theory does make predictions beyond the landscape, specific mathematical structures, specific relationships between quantities, specific results in contexts where string theory can be tested indirectly. The ADS/CFT correspondence, a precise mathematical duality discovered by Juan Maldacena in 1997, relating a string theory in a particular curved spacetime to a quantum field theory on its boundary, has produced testable predictions in contexts far from high-energy particle physics, including in condensed matter physics and the behavior of strongly coupled plasma. It is perhaps the most studied and verified result in all of theoretical physics, even though the specific string theory it involves is not the one describing our universe. String theory has also absorbed its apparent competitors. In the 1990s, 5 distinct string theories had been developed, each mathematically consistent, each superficially different. The existence of 5 separate theories rather than one seemed problematic. A theory of everything should presumably be unique. Edward Witten showed in 1995 that all 5 string theories are different limiting cases of a single 11-dimensional theory, which he called M-theory. What M stands for, membrane, matrix, mystery, Mother Witten left ambiguous. M-theory is not fully formulated. Its complete mathematical description does not yet exist. It is more a framework and a set of relationships between known theories than a finished edifice. The theory of everything is, at the moment, a theory of almost everything, in some limits, in certain dimensions, with the full structure still under construction. Whether string theory is correct, physically, is genuinely unknown. It may be that the extra dimensions are real and will eventually be detected through subtle effects at particle accelerators or in gravitational wave astronomy. It may be that the theory correctly describes quantum gravity and will eventually make predictions that are confirmed. It may be that the landscape is real, the multiverse is real, and string theory provides the deepest available description of why the universe has the properties it does. Or it may be that string theory is a beautiful mathematical structure that does not describe the actual universe, a path that revealed extraordinary mathematics without being the path to physical truth. Both outcomes have precedence in the history of physics. What is not in question is the mathematical depth of the structure string theorists have explored. The discoveries made within string theory, the dualities, the correspondences, the unexpected connections between seemingly unrelated physical systems have transformed large areas of mathematics and theoretical physics, regardless of the theory's ultimate physical validity. Physicists working on string theory have solved mathematical problems that mathematicians had failed to crack for decades, discovered connections between areas of mathematics that appeared completely unrelated, and produced a body of work that has enriched human understanding of abstract structure in ways that will persist regardless of whether strings are real. The universe may or may not be made of strings, but the attempt to find out has revealed something about the architecture of mathematics itself, the deep structure of the possible that seems to point toward something real, even if what it is pointing at has not yet fully come into focus. Everything vibrates. Atoms vibrate. Molecules vibrate. The electromagnetic field oscillates. Space-time itself, as gravitational wave astronomy has now confirmed, can be made to ripple and ring. The universe is not, at its deepest level, a collection of static things. It is a collection of processes, of motions, of oscillations in fields and geometries that interact and evolve across time. String theory says these vibrations go all the way down, that beneath the quarks and electrons, beneath the quantum fields, beneath the Planck scale, where space and time themselves may dissolve into something more fundamental, there is one more layer, one more vibration, a string, playing the only song it knows, in dimensions we cannot see, at scales we cannot reach, in a register so far below the threshold of any instrument that we may never hear it directly, only infer it, from the music it makes at the scales we can see. The simulation hypothesis. What if none of this is real? Not as a passing thought. Not as the kind of idle speculation you entertain for a moment, and then set aside because the coffee is ready or someone is calling your name. As a genuine, seriously considered, philosophically and scientifically examined possibility that the universe you experience, the stars, the galaxies, the 14 billion years of history reconstructed across this series of reflections, the body you inhabit, the consciousness doing the inhabiting, is not the base layer of reality, but a constructed one, a simulation, a computational process running on some substrate that exists outside everything you have ever observed or could observe. This is not a new idea dressed in modern clothing. The suspicion that experienced reality might not be the deepest reality is ancient. Plato's allegory of the cave prisoners watching shadows on a wall, mistaking the shadows for reality, while the true forms casting them remain unseen, is a version of this thought. Descartes, in the 17th century, systematically doubted everything that could be doubted and arrived at the possibility of an evil demon deceiving him about the entire nature of reality. Hindu and Buddhist philosophical traditions contain sophisticated discussions of Maya, the illusory nature of the phenomenal world, the possibility that what we experience as solid reality is a kind of projection or appearance, rather than ultimate truth. What is new is the specific technological framing, and the argument that makes it more than metaphor. In 2003, philosopher Nick Bostrom published a paper presenting what is now called the simulation argument. It is a trilemma, a structure presenting three possibilities, at least one of which must be true. The first possibility: virtually all civilizations at our current level of technological development go extinct before reaching the capability to run realistic simulations of conscious minds. They either destroy themselves or hit a development ceiling, or face some other filter that prevents them from reaching what Bostrom calls technological maturity. The second possibility: virtually all technologically mature civilizations, those capable of running such simulations, choose not to. Whether from ethical constraints, lack of interest, or some universal convergence of values that makes running ancestor simulations unappealing, the simulations simply do not get run in any significant number. The third possibility: we are almost certainly living in a simulation right now. The logic is as follows. If civilizations regularly reach technological maturity and choose to run detailed simulations of minds or universes, they would run an enormous number of them, potentially billions or trillions of simulated realities for every base reality. In that case, simulated minds would vastly outnumber non-simulated ones. And any given mind, including yours, would be statistically far more likely to be one of the many simulated minds than one of the rare non-simulated ones. If possibility 1 and 2 are both false, if civilizations do reach maturity and do run simulations, then possibility 3 follows with near certainty from pure probability. You have to eliminate one of the 3. Either almost everyone dies before building the technology, or almost everyone who builds it decides not to use it, or you are in a simulation. The argument does not tell you which one is true, it tells you that at least one must be, and it does so without requiring any assumption about the nature of consciousness or the specific technology involved, only that sufficiently advanced computation can produce sufficiently realistic, simulated experience, which is itself a significant assumption, but not obviously false. Physicists have examined the simulation hypothesis from a different angle. If the universe is a simulation, what might we expect to observe? Simulations, regardless of their sophistication, presumably run on finite computational resources. And finite computational resources imply limits a resolution below which the simulation does not render detail, a maximum precision at which physical quantities are defined, a granularity to space-time below which the concept of distance or duration becomes meaningless. Physics already has such a scale. The Planck length, approximately 10 to the power of -35 meters, is the scale at which quantum gravitational effects are expected to become significant, where the smooth space-time of general relativity is expected to break down into something more granular. Below this scale, current physics makes no reliable predictions. Some researchers have noted that a universe with a fundamental minimum length scale is precisely what a pixelated simulation would look like from the inside, a computational substrate that renders detail only down to a certain resolution, below which there is simply nothing more to render. This is not evidence that the universe is a simulation. It is an observation that one of the universe's known properties is consistent with what a simulation would produce. Consistency is not confirmation. The Planck scale may exist for reasons entirely unrelated to computation, but the observation is not without interest. The speed of light presents a similar observation. A simulation running on a finite processor might impose a maximum information transfer rate at a speed limit on how fast states in one region of the simulation can influence states in another, determined by the computational architecture rather than by any deeper physical principle. The speed of light is such a limit, universal, absolute, apparently fundamental. Whether it is fundamental for deep physical reasons or fundamental because it is a computational constraint is not a question current physics can answer. More intriguingly, quantum mechanics already describes the universe as behaving differently depending on whether it is being observed. The wave function collapses upon measurement. Unobserved particles exist in superpositions of multiple states simultaneously, resolving to definite values only when an interaction occurs that records information about them. In the many worlds interpretation, this is a branching of reality. All outcomes occur. In the Copenhagen interpretation, there is genuinely no definite state before measurement. In either case, the universe appears to compute to resolve only what is being observed, and leaves the rest in a kind of probabilistic suspension. A simulation optimized for computational efficiency might do exactly this, rendering only what is being observed in detail, leaving the unobserved regions in an unresolved state that requires less computational resources, resolving detail on demand when an observer interacts with a region of the simulation. This is not how we believe the universe works. Quantum superposition is understood as a physical state, not a computational shortcut, but the structural similarity between a computationally efficient simulation and the observer dependence of quantum mechanics has been noted by people who are not cranks. The hardest question the simulation hypothesis raises is not scientific, it is philosophical, and it is this: if the simulation is sufficiently detailed, if the physics inside it is consistent, the history coherent, the experiences of its inhabitants genuine, does it matter? If everything you have ever felt, thought, loved, feared, and lost is real within the simulation, if your consciousness is genuinely experiencing, if your pain is genuinely felt, and your joy genuinely felt, and the people you care about are genuinely there with you, does the existence of a substrate outside the simulation change anything that matters about your existence? Plato's cave prisoners were missing something, the real forms outside the cave. But in a simulation with no exits, with no possibility of accessing the base reality, the situation is different. The simulation is not a shadow of something more real you are being denied access to. It is simply the reality in which you exist. Its being computed rather than base-level physical would not make your experiences less real as experiences. It would not make your relationships less genuine. It would not make the universe's history, the 14 billion years of physics and chemistry and biology that produced you, less extraordinary. It would simply mean that the universe has a different kind of bottom, not quantum fields or strings or some other physical substrate, but computation, information, process, which raises its own profound question, one that loops back to the origin of everything discussed in this series. If the universe is a simulation, what is the nature of the computer running it? What are the physical laws of the base reality from which our reality is generated? What is the energy source powering the computation? How long has it been running? Was it started deliberately, or did it emerge spontaneously? Is there a programmer? Is the programmer aware of what the simulation has produced? Aware, specifically, that within it, a small rocky planet developed life, that developed consciousness, that developed science, that eventually looked up at the stars and wondered whether any of it was real. And did the programmer, if there was one, anticipate that moment? Or were they, too, surprised? These questions have no answers, not because we haven't looked hard enough, because the answers, if they exist, are outside the system, outside the universe, outside causality as we understand it, outside the reach of any observation or experiment that could ever be performed from within the simulation. The simulation hypothesis, if true, places the most important questions about the nature of reality permanently beyond reach, which is perhaps the most unsettling thing about it. Not that you might be living in a simulation, but that you could be, and you would never know, and lying here, in the dark, inside a universe that behaves consistently and beautifully and according to elegant mathematical laws, surrounded by a history stretching back 14 billion years and forward into a future of almost unimaginable length, the question of whether this is the base reality or a constructed one changes nothing about the weight of your body against the surface beneath you. Nothing about the sound of your breathing. Nothing about the fact that you are here. Whatever here is. The end of everything. Everything that has ever existed will eventually be gone. Not transformed, not recycled into something new. Gone, in the most complete and final sense that physics allows, dispersed into a cold, featureless equilibrium from which no structure, no complexity, no process resembling life or thought or experience can ever re-emerge. The universe began in a moment of extraordinary order. It will end if end is even the right word for a process so slow it makes every other time scale in this series look like a heartbeat in a stillness so total that the word silence fails to carry its weight. But before we reach that stillness, there is an inventory to take. Because the end of everything is not a single event. It is a sequence, a long, slow, hierarchical dismantling of structure, proceeding from the smallest and most fragile to the largest and most enduring, each category of thing persisting for its allotted span before the physics of entropy and time claims it. And to understand what will be lost, it helps to move through that sequence carefully and to feel the weight of each loss before moving to the next. Begin with the most immediate. The Sun will exhaust its hydrogen fuel in approximately 5 billion years. In the final stages of its life, it will expand into a red giant, its outer envelope swelling to engulf the inner planets. The oceans will boil away billions of years before this, as the Sun gradually brightens on its main sequence. The increased energy reaching Earth will trigger a runaway greenhouse effect that drives water vapor into the upper atmosphere, where ultraviolet radiation breaks it apart. The hydrogen escapes into space. The oceans do not evaporate in the sense of becoming clouds. They are destroyed, the water molecules themselves dismantled, the hydrogen lost to space, the oxygen remaining as a trace in a desiccated, scorched atmosphere above a surface that has not known liquid water for hundreds of millions of years. Long before the Sun becomes a red giant, Earth will no longer be Earth in any meaningful sense. What will be lost with the oceans is everything that depends on them: the carbon cycle, the weather, the hydrological system that has moved water from sea to sky to land and back for 4 billion years, the marine ecosystems that harbor the majority of Earth's biomass, the chemical buffering that has kept the atmosphere and surface habitable through ice ages and warm periods and mass extinctions. Everything that makes Earth the particular, improbable, living world it is today is downstream of liquid water. When the water goes, everything goes with it. If anything of human civilization survives, whether biological descendants, machine successors, or something unimaginable, from our current vantage, it will not survive on Earth. Not because of catastrophe. Simply because the star that made Earth habitable will outgrow the distance at which it gave life rather than taking it. The Sun will become a white dwarf, a slowly cooling ember, roughly the size of Earth, radiating its stored heat into an increasingly cold cosmos. It will persist for trillions of years in this form, not burning, not fusing, simply cooling. And the solar system, or what remains of it, will orbit this dim remnant star. Cold, dark, airless world circling a dying light. The orbital mechanics unchanged by the catastrophic changes in the star at the center. There is something in that image worth pausing on. The planets, or whatever remains of them, will continue orbiting. The same gravitational relationships that have structured the solar system for 4.5 billion years will persist long after the star at the center has stopped shining. The orbits are almost perfectly preserved by the conservation of angular momentum, indifferent to what happens to the bodies involved. The solar system as a gravitational structure will outlast the solar system as a living one by an enormous margin of time. Galaxies will continue their mergers and evolutions across the next hundreds of billions of years. The collision of the Milky Way and Andromeda 4.5 billion years from now, will produce Milky Way, a large elliptical galaxy containing the remnants of both. Star formation will continue for a while, fueled by gas compressed in the collision. New stars will ignite, burn, and die. But the gas supply is finite. The mergers and interactions that trigger star formation eventually cease as the gas is consumed. The great elliptical galaxies of the far future will be populated almost entirely by aging and dying stars, the blue light of young stars absent, replaced by the dim red glow of the longest lived. Then those go out too, the last star a red dwarf, somewhere in what was once a galaxy. Now a dark collection of stellar remnants will exhaust its fuel and fade. The lights go out across the universe, not simultaneously but sequentially. The smallest and most fuel-efficient lasting longest, the universe dimming over trillions of years, rather than in a single moment. There is no announcement, no final flare that marks the death of the last star. It simply dims and cools and joins the population of cold, dark objects that constitute the matter of the universe after the age of stars is over. What will be lost with the last star is light. Not permanently. The Hawking radiation of black holes produces photons, and the thermal radiation of cooling stellar remnants persists for an enormously long time. But effectively, experientially, the universe will become dark in a way it has not been since before the first stars ignited, 200 million years after the Big Bang. The cosmic dark ages that preceded the first stars lasted 200 million years. The darkness that follows the last star will last in some form until the last black hole evaporates. That is a span of time measured in numbers with 100 digits. The black holes will persist through the darkness. Supermassive black holes, the ones at the centers of galaxies, containing billions of solar masses, will endure longest, evaporating via Hawking radiation on timescales of 10 to the power of 100 years. During this period, the universe will be almost entirely empty. The matter that once formed stars and planets and living things dispersed into a thin gas of particles and radiation. The only significant structures, the slowly shrinking black holes radiating their faint Hawking glow into the void. And then those too will go. The final evaporation of the last black hole will be, in a sense, the last event. The last occurrence of a physical process energetic enough to be called an event in any meaningful sense. A burst of high-energy Hawking radiation, the mass energy of a black hole that once contained billions of suns releasing itself in a final flash, and then nothing. Nothing except the cold, expanding, thermal equilibrium universe stretching outward forever. The photons and particles that remain spreading thinner and thinner as space continues to expand, the temperature dropping asymptotically toward absolute zero, but never quite reaching it. The universe persisting in a state that is technically alive, still existing, still expanding, but from which no process, no structure, no event of any significance can ever again emerge. This is the state discussed in the section on heat death, but it is worth approaching it differently here, at the end. Because what the heat death represents, what the end of everything actually means, is not the end of existence. The universe will continue to exist in some sense. Space will continue to expand. The remnant particles will continue to move. The laws of physics will continue to apply to a universe in which they no longer produce anything. What ends is meaning, not in any mystical sense, in a specific, precise, thermodynamic sense. Meaning requires structure. Structure requires energy gradients. Energy gradients require the flow of energy from concentrated sources to dispersed sinks. The universe began with an extraordinary concentration of energy, the Big Bang singularity, the lowest entropy initial state, and has been spending that initial endowment ever since, converting order into disorder, structure into diffusion, concentrated energy into dispersed thermal equilibrium. Every star that burned was spending some of that endowment. Every chemical reaction, every geological process, every living thing that metabolized food into movement and thought, all of it drawing on the original investment of order that the Big Bang provided. And when that endowment is fully spent, when entropy has reached its maximum and all gradients have been smoothed away, the spending stops. The process ends. Not the universe, the process. Here is the inventory of what will be lost: oceans, continents, weather, seasons, the smell of rain, the sound of wind. Every ecosystem that has ever existed, and every one that will exist before the sun takes them. Every language, every piece of music ever composed, every memory stored in any mind, biological or otherwise, that does not find a way to persist. The starry night sky first dimming over trillions of years as the remaining stars exhaust themselves, then going dark entirely. The warmth of sunlight on any surface. The chemical complexity that makes life possible. The information contained in the genetic sequences of every species that has ever lived, already largely lost to extinction, and eventually lost entirely as the molecules that carry it break down past any possibility of recovery. Every thought that has ever been thought. Every face that has ever been loved. Every question that has ever been asked about the nature of the universe, including this one, including the one that produced this series of reflections, including the particular mind lying in the dark right now, in the brief, warm window between the universe's birth and its long cooling, asking where everything came from and where it is going. All of it eventually gone. And yet, the fact that it ends does not change what it was. The 14 billion years of cosmic history that produced you the Big Bang, the first stars, the supernovae that seeded the galaxy with heavy elements, the formation of the solar system, the 4 billion years of life evolving on a rocky planet, the improbable chain of extinctions and survivors and mutations and accidents that produced a mind capable of lying still and contemplating its own existence, that history is not diminished by the fact that it ends. A story is not less real for having a final page. A fire is not less warm for eventually going out. The universe spent 14 billion years building the conditions for complexity. It spent 4 billion years on this planet alone, refining chemistry into biology, biology into awareness, awareness into something capable of asking the questions this series has been circling from the beginning. Why is there something rather than nothing? What is consciousness, and why does it exist? Are we alone? What came before the beginning, and what comes after the end? These questions have no final answers. They may never have final answers. But the fact that they are being asked, that the universe, through the particular improbable arrangement of matter that constitutes a human mind, has become capable of examining itself, is not nothing. It is, in some sense, everything. The universe is not aware of its own end. It does not dread the heat, death, or mourn the last star, or feel the loss of the last black hole's evaporation. It simply proceeds according to its laws, spending its initial endowment of order, moving from structure to diffusion with the patient indifference of physics. Only we know what is coming. Only we, the brief, fragile, extraordinarily lucky arrangements of matter that evolution produced in the last eye blink of cosmic time, have the particular curse and gift of being able to see the whole arc, to know the beginning and anticipate the end, to hold the entire story in a mind that is itself part of the story, that emerged from the story, and that will eventually return to the diffuse, undifferentiated matter from which all stories are made. You are the universe knowing itself. For a moment, in the dark, in the thin, warm window between the first light and the last, that moment is now. It will not come again.